You are falling through a hole in space right now, and you have been your entire life. It is 2 billion light-years wide. It surrounds our galaxy, our local cluster, everything within 1 billion light-years of Earth. Scientists confirmed it in 2013. They named it the KBC Void, and the discovery should have rewritten every cosmology textbook on the planet. Instead, it got buried under polite academic silence and a few journal articles most people will never read. But here is the thing. This void is not just a curious footnote about empty space. It is actively breaking the rules. It is making the universe appear to expand faster than it should. It is sitting at the exact center of one of the biggest crises in modern physics, a problem so severe that Nobel Prize winners are openly admitting we may have misunderstood the fabric of reality itself. They call it the Hubble Tension, and the KBC Void might be the reason it exists. For decades, cosmologists assumed the universe was more or less the same everywhere, uniform, predictable. Galaxies scattered like stars across a cosmic web of matter and energy. That assumption held together every equation we use to describe the birth, expansion, and fate of everything. Then Ryan Keenan, Amy Barger, and Lennox Cowie started counting galaxies. What they found was not uniform. What they found was a desert, a region of space where matter is 20% thinner than it should be, where 90% of the volume around us is essentially hollow, where the gravity is so weak that dark energy dominates and the local expansion rate does not match the rest of the universe. We thought we understood our place in the cosmos. Turns out, we have been standing in a hole the entire time. And that changes everything. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We thought we had the universe figured out. Not completely, not arrogantly, but enough. Enough that the basic story made sense. Enough that the equations worked. Enough that when you pointed a telescope at a random patch of sky and counted the galaxies, the numbers lined up with what the theory predicted they should be. For the better part of a century, cosmology had been running on a framework so successful, so consistently validated by observation after observation, that it had earned the right to be called standard. The standard model of cosmology, capital S, capital M, like it meant something. And it did. The story it told went like this. About 8 billion years ago, the universe began. Not in a place, because there was no place yet. Not at a moment you could point to on a clock, because time itself started ticking in that instant. Everything that exists, every atom, every photon, every cubic centimeter of empty space, erupted from a state of unimaginable density and temperature. We call it the Big Bang, though that name makes it sound like an explosion in a room, when it was actually the sudden appearance of the room itself, expanding in all directions at once, cooling as it grew. For the first 380,000 years, the universe was a fog. Particles collided so violently that light couldn't travel more than a few steps before smashing into something else. Then the fog cleared. The universe cooled enough for atoms to hold themselves together, and light finally had room to move. That light is still moving. We can see it today, stretched and faded by 13 billion years of cosmic expansion, arriving as a faint microwave glow from every direction at once. Astronomers call it the cosmic microwave background, and it's the oldest thing we can observe. A photograph of the infant universe, blurry and uniform, with tiny ripples of temperature marking where matter had started to clump just slightly more in some places than others. Those ripples mattered a lot because gravity amplifies inequality. Anywhere the matter was even a fraction denser than average, it pulled harder on the gas around it. Dense regions got denser. Thin regions got thinner. Over hundreds of millions of years, the ripples grew into clouds of hydrogen. The clouds collapsed into stars. Stars gathered into galaxies. Galaxies gathered into clusters. And the clusters strung themselves along invisible threads of dark matter, the mysterious substance that makes up about 85% of the mass in the universe, but refuses to emit, absorb, or reflect light. We only know dark matter exists because galaxies move as if they're embedded in something much heavier than the stars we can see. The gravity is there, the matter doing the pulling is not. By the late 1990s, astronomers had added a third ingredient to the recipe: dark energy. In 1998, two independent teams were measuring distant supernovae, trying to figure out how much the expansion of the universe was slowing down under the pull of all that matter. Gravity, after all, is attractive. It should be reeling everything back in, not by much, but measurably. The measurements came back wrong. The universe wasn't slowing down, it was speeding up. Something was pushing galaxies apart, overpowering gravity on the largest scales, and whatever that something was, it made up roughly 68% of everything. Dark energy joined dark matter and ordinary matter as the third pillar of the Standard Model. 3 ingredients, 1 universe. About 5% normal stuff, the atoms that make stars and planets and people. About 27% dark matter, the invisible scaffolding holding galaxies together. And about 68% dark energy, the accelerator pedal driving expansion faster every billion years. That framework, messy as it sounds, worked beautifully. Plug those percentages into the equations of general relativity. Add the initial conditions from the cosmic microwave background, and you could predict what the universe should look like at any point in its history, how fast galaxies should be moving, how they should be distributed in space, how large the biggest structures should be, when the first stars should have lit up. The predictions matched reality so well that by the early 2000s, cosmology had entered what some researchers half-jokingly called a golden age. A time when the big questions had clear answers, and the remaining work was about filling in details, not overturning foundations. And then there was the cosmic web. This is where the universe stops looking like a smooth soup and starts looking like something organic. In the 1980s, astronomers began mapping galaxies in 3 dimensions, recording not just where they appeared on the sky, but how far away they were. The tool they used was redshift, the stretching of light caused by cosmic expansion. The further a galaxy is, the faster space is carrying it away from us, and the more its light gets stretched toward the red end of the spectrum. Measure the redshift, calculate the distance, plot the position. Do that for thousands of galaxies, and a pattern emerges. Galaxies are not scattered randomly. They line up along filaments, vast threads of matter stretching across hundreds of millions of light years. Where filaments intersect, you get nodes, dense clusters where hundreds or thousands of galaxies pile up under their combined gravity. Between the filaments there is almost nothing, voids, enormous bubbles of empty space where galaxies are rare and the density of matter drops to a fraction of the cosmic average. By the late 1980s and early 1990s, surveys like the CFA Redshift Survey and the 2-degree Field Galaxy Redshift Survey had mapped enough of the sky to confirm the structure. The universe on its largest scales looks like a sponge, or a foam, or a web, depending on which metaphor you prefer. Filaments, walls, nodes and voids repeating across billions of light years in every direction. The voids were not a surprise. Simulations of structure formation in a dark matter-dominated universe had predicted them. As matter clumped into filaments under gravity, It had to leave gaps behind. The voids are where the matter used to be before it drained into the denser regions. Think of it like a bathtub. Open the drain and the water flows toward the hole, leaving a thin film on the sides. The voids are the thin film. Most of the mass has gone elsewhere. Typical voids measure somewhere between 30 and 150 million light-years across. Some are smaller, a few are bigger, but the size distribution follows a predictable pattern, and the largest voids ever found topped out at maybe 300 or 400 million light-years, which was big but not alarming. The standard model could accommodate that. There was also an assumption baked into cosmology so deeply that most people didn't even think to question it: the cosmological principle. Formalized in the 1930s, it states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. No special locations, no preferred orientations. Zoom out far enough, past the clumps and voids and filaments, and the universe should smooth out into a featureless average. The consensus was that this smoothing happened at scales larger than about 300 million light-years. Below that, you'd see structure. Above that, uniformity. Cosmology as a science depends on that principle. If the universe is lumpy and uneven on the largest scales, then the equations stop working. The math assumes you can treat the cosmos as a smooth fluid with small perturbations on top. If the perturbations aren't small, the whole framework wobbles. For decades, observations supported the principle. The cosmic microwave background, the most distant thing we can see, is smooth to 1 part in 100,000. Galaxy surveys showed structure on small and medium scales, but when astronomers averaged over volumes larger than a few 100 million light-years, the density evened out. Everything fit. The universe was weird, sure. Dark matter, dark energy, an accelerating expansion that defied intuition. But it was consistently weird, predictably weird, the kind of weird you could build a career on. Then came the glitches, small ones at first, easy to ignore, easy to explain away as noise or bad data, or the kind of statistical flukes that happen when you're surveying billions of galaxies. But they kept showing up. In 2003, astronomers analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, noticed something odd in the cosmic microwave background: a cold spot, a region roughly 10 degrees across, about 20 times the width of the full moon, where the temperature was slightly lower than the surrounding sky, not by much, a difference of a few millionths of a degree. But it was there, sitting in the southern hemisphere of the microwave sky like a bruise on an otherwise smooth surface. Cold spots in the cosmic microwave background are not inherently strange. The whole map is covered in hot and cold patches. That's the ripple structure, the seeds of galaxies. But this particular cold spot was larger and colder than the statistical models predicted it should be. If you ran simulations of 1 million random universes starting from the same initial conditions, only a handful would produce a cold spot that size. Some researchers proposed it might be a void, not a void in the distribution of galaxies nearby, but a supervoid, an enormous underdense region sitting between us and the cosmic microwave background, somewhere around 3 billion light-years away. As microwave photons travel through a void, they lose a tiny bit of energy climbing out of its gravitational well. If the void is big enough, the effect adds up. The photons arrive slightly cooler, imprinting a shadow on the map. The math worked, but the void required to explain the cold spot would have to be absurdly large, more than 1 billion light-years across. Big enough to make cosmologists uncomfortable because voids that size push right up against the edge of what the cosmological principle allows. Then there were the peculiar velocities. In principle, Galaxies should move in a way that reflects the local gravitational landscape. They fall toward dense regions and drift away from voids, all while being carried along by the overall expansion of space. The expansion part is smooth and predictable. It's called the Hubble flow, and it gives you a clean relationship between distance and velocity. Measure how far a galaxy is, multiply by the Hubble constant, and you know how fast it should be receding. Except galaxies don't follow the script exactly. They also have peculiar velocities, small deviations from the Hubble flow caused by the tugging of nearby mass. Usually those deviations are modest, a few hundred kilometers per second at most. By the mid-2000s, surveys like the Sloan Digital Sky Survey were mapping the velocities of tens of thousands of galaxies with enough precision to measure those deviations, and some of them were not modest. Galaxies in certain regions were moving hundreds of kilometers per second faster or slower than the Hubble flow predicted. That alone wasn't shocking. Massive galaxy clusters can pull on their neighbors, but when researchers tried to account for all the visible mass, all the dark matter halos inferred from gravitational lensing, the numbers didn't quite close. There seemed to be large-scale flows, coherent motions of galaxies across volumes hundreds of millions of light-years wide, drifting in directions that didn't match the distribution of matter anyone could see. Some called it the dark flow. Others were more cautious, noting that measuring peculiar velocities is hard and the data could be contaminated by systematic errors. Still, the unease was growing. Then in 2008 and 2010, redshift surveys covering large volumes of space started showing something subtler but harder to dismiss. When astronomers counted galaxies in spheres of increasing radius centered on the Milky Way, the density didn't even out the way it was supposed to. Out to about 300 million light-years, galaxies were slightly less common than the cosmic average. Not wildly less, maybe 15 or 20% below the mean, but the deficit was consistent across multiple surveys using different telescopes and different methods. It wasn't a fluke in one dataset, it was a signal that kept reappearing. At first, nobody called it a void. The word void carried implications. It suggested something large, something significant, something that might challenge the standard model. So people called it a local underdensity, a depression in the cosmic web, a region where by chance fewer galaxies had formed. Voids were common after all. We happened to live near one, unlucky maybe, in terms of having a less crowded neighborhood, but not cosmologically meaningful. Except the underdensity wasn't small, it wasn't a minor dip, it extended in all directions. And the Milky Way wasn't sitting on the edge of it, which would have been easier to explain. We were near the center. That should not have been possible. Or rather, it should have been possible but extremely unlikely. If the universe is homogeneous on large scales, then any randomly chosen galaxy should find itself in an average environment when you zoom out far enough. Sure, you might be in a void or a filament, but those features should be local. Draw a sphere 500 million light-years wide around yourself, and the density inside that sphere should match the cosmic mean. Draw a sphere 1 billion light-years wide, and the match should be even closer. The Milky Way's sphere wasn't matching. The larger the sphere, the more the deficit persisted. By 2010, cosmologists had a term for the phenomenon: the local hole. Not a void yet, just a hole, a place where the universe seemed to have forgotten to put as much stuff as it should have. Some researchers tried to downplay it. Measuring the density of the universe is hard. You have to account for selection effects, for the fact that faint galaxies are harder to detect at large distances, for the possibility that dust or foreground objects are blocking your view. Maybe the surveys were missing galaxies, maybe the statistical analysis was flawed. Maybe the underdensity would disappear once better data came in. That was the hope anyway. Because if the underdensity was real, if it extended out past 1 billion light years in every direction, then the Milky Way was sitting in the middle of the largest cosmic structure ever observed, and structures that large were not supposed to exist. The cosmological principle was not just a philosophical nicety, it was load-bearing. The entire framework of modern cosmology, the equations that describe how space expands, how matter clumps, how the cosmic microwave background formed, all of it assumes that the universe is statistically uniform on the largest scales. If you allow for giant anomalies, regions 1 billion light-years across where the density is 20 or 30% off from the mean, then you're not living in a homogeneous universe anymore. You're living in a universe with geography, and geography breaks the math. Cosmologists use something called the Friedmann equations to model the universe's expansion. Those equations assume a smooth, uniform distribution of matter and energy. If the distribution is lumpy at large scales, the equations give you the wrong answer. Not a little wrong, fundamentally wrong. The expansion rate you calculate depends on the density around you. If you're sitting in an underdense region, space expands faster locally than it does in the denser parts of the universe. Your measurements of the Hubble constant, the number that tells you how fast the cosmos is flying apart, would be skewed. You'd think the whole universe was expanding at the rate you measure nearby, but you'd be wrong. You'd be measuring the expansion rate of your local hole, not the universe at large. And that brings us to the other glitch, the one that by 2010 was starting to feel less like a nuisance and more like a crisis. The Hubble constant, the single number that describes how fast the universe is expanding right now, had split into 2 different values depending on how you measured it. Teams using the cosmic microwave background, looking backward to the early universe and running the standard model forward, were getting a value around 67 kilometers per second per megaparsec. Teams measuring nearby galaxies directly, using supernovae and variable stars as distance markers, were getting 73, a gap of nearly 9%. In a field where measurements are usually precise to within a percent or two, a 9% discrepancy is not a rounding error. It's a signal that something is off. Either one of the measurements is wrong, or the model connecting them is incomplete. Nobody knew which. But by 2010, a handful of researchers were starting to wonder whether the local underdensity and the Hubble tension were connected. If the Milky Way was sitting in a region where space was expanding slightly faster than average, then the local measurements of the Hubble constant would come out high, not because the instruments were bad, not because the astronomers made a mistake, but because they were measuring the expansion rate of an underdense bubble and mistaking it for the expansion rate of the entire universe. If that was true, then the solution to the Hubble tension wasn't better telescopes or more precise data. It was geography. We were lost, and we didn't know it yet. The pieces were in place, the cold spot in the microwave background, the peculiar velocities, the local underdensity stretching out past hundreds of millions of light-years, the Hubble tension that refused to go away. None of it was loud enough on its own to overturn the standard model, but taken together, the glitches were pointing in the same direction, towards something large, something we were inside, something that was bending our view of the cosmos in ways we hadn't accounted for. The universe had been trying to tell us for years, we just hadn't been listening. Then in 2013, someone finally looked at the data and said it out loud. We are living inside a giant hole. The story of how we discovered we were living inside a cosmic hole starts not with a telescope pointed at the sky, but with a problem. A measurement problem, a weird, stubborn, increasingly annoying gap between what the numbers said the universe should look like up close and what it actually looked like when you counted the galaxies in our neighborhood. By the early 2010s, that gap had widened from a curiosity into something harder to ignore. Surveys kept coming back with the same message. There are fewer galaxies around us than there should be, not just in one direction, in every direction, out to distances where the deficit should have averaged away into cosmic noise. It was still there, quiet, persistent, wrong. Ryan Keenan was a graduate student at Harvard in 2011 when he started pulling together galaxy survey data from multiple sources, trying to quantify exactly how wrong the local density was. Keenan wasn't looking for a void. He was trying to solve a different problem entirely, one involving the faint wisps of hydrogen gas that fill the space between galaxies. To study that gas, he needed an accurate map of where galaxies were and weren't, so he could tell whether the gas was sitting in dense regions or sparse ones. The map he built to answer that question ended up answering a much larger one. He wasn't working alone. Amy Barger, a professor at the University of Wisconsin-Madison with a reputation for meticulous data analysis, and Lennox Cowie, an astronomer at the University of Hawaii who had spent decades mapping distant galaxies, joined the effort. The three of them, Keenan, Barger, and Cowie, began compiling redshift measurements from every major galaxy survey that covered the nearby universe, redshifts from optical telescopes, redshifts from infrared surveys, data from X-ray observatories tracking galaxy clusters, radio surveys picking up emissions from neutral hydrogen. They layered it all together into a three-dimensional map spanning billions of light-years, with the Milky Way sitting at the center. What they were doing wasn't glamorous. It was bookkeeping, data hygiene, the kind of work that doesn't make headlines because it involves spreadsheets and error bars and long arguments about whether a particular galaxy's redshift measurement is reliable or contaminated by foreground noise. But it's the kind of work that catches things other people miss, and what Keenan, Barger, and Cowie caught was a whole. A massive, undeniable, 2 billion light-year-wide deficit in the distribution of galaxies stretching out from the Milky Way in every direction. The key breakthrough wasn't a new telescope or a new instrument, it was scope. Previous studies had looked at slices of the sky, narrow pencil beams pointing outward, or shallow surveys covering wide areas but not reaching very far. Keenan's team combined deep and wide. They stitched together data from surveys that had been designed for completely different purposes, creating a composite map with enough volume and enough distance coverage to see the full extent of the underdensity. And once you could see the whole thing, it stopped looking like a statistical fluctuation. It looked like structure. They measured the galaxy density in spherical shells at increasing distances from the Milky Way. Close in, within about 50 million light-years, the density was normal. Our local neighborhood, the so-called local group containing the Milky Way, Andromeda, and a few dozen smaller galaxies, sat at roughly the cosmic average. But step outward past 100 million light-years, and the density started dropping. By 300 million light-years, it was 15 to 20% below the mean. By 500 million light-years, 20 to 30% below. And it stayed low, all the way out past 1 billion light-years. The deficit persisted. Fewer galaxies, fewer galaxy clusters, less matter. It wasn't a void in the traditional sense, a nearly empty bubble with a sharp boundary. It was a gradual underdensity, a depression in the cosmic web that extended so far in every direction that the Milky Way sat near its center. That last part was the problem. Sitting near the center, voids are common in the universe. The cosmic web is full of them, bubbles where matter has drained away into the surrounding filaments. But those voids have edges. If you're sitting in a typical void, you're either near the wall where galaxies start piling up again, or you're drifting somewhere in the middle with a clear sense of which way is out. The Milky Way wasn't near a wall. The underdensity extended roughly the same distance in every direction: north, south, east, west, up, down. Wherever you pointed, the galaxy count stayed low for about 1 billion light-years before climbing back toward the cosmic average. That symmetry, that centrality made the structure look less like a random feature and more like a cosmic address. We weren't just near a void, we were inside one, and it was enormous. In 2013, Keenan, Barger and Cowie published their findings in the Astrophysical Journal. The paper was titled "Evidence for a 2 billion light-year radius void in the local universe." The language was cautious, the way scientific papers always are when they're reporting something that shouldn't exist, but the numbers were clear. Within a sphere roughly 1 billion light-years in radius, centered on the Milky Way, the density of galaxies was 20 to 50% below the cosmic mean. The total diameter of the underdense region was about 2 billion light-years, making it the largest cosmic structure ever identified, not the largest object. Objects have boundaries and interiors. This was a deficit, a place where the universe had less stuff than it was supposed to. They called it the KBC Void, initials for Keenan, Barger and Cowie. Not because they were interested in putting their names on a map, but because astronomers needed something to call it, and the alternative, that giant hole we're sitting in, wasn't going to fit in a journal title. The reaction from the cosmology community was mixed. Some researchers accepted the findings almost immediately. The data was solid, the methods were sound. The underdensity had been hinted at in previous surveys, and Keenan's team had simply done the work to confirm it at high confidence. Others were skeptical, not because the analysis was flawed, but because the implications were uncomfortable. A void 2 billion light-years wide pushes right up against the limits of what the cosmological principle allows. According to the standard model, the universe should smooth out at scales larger than about 300 million light-years. Structures significantly larger than that are supposed to be rare. A 2 billion light-year void isn't just rare. It's a statistical outlier so extreme that some models predicted it should occur less than once per observable universe. Think about that for a second. The observable universe is vast. It contains roughly 2 trillion galaxies spread across a sphere 93 billion light-years in diameter. If a structure as large as the KBC Void is a one-in-a-universe event, and we happen to be sitting inside it, then either we are extraordinarily unlucky or the models predicting how rare such structures should be are missing something. Neither option is comforting. The first implies that our measurements of the cosmos are biased by our location in a way we can't easily correct for. The second implies the standard model of cosmology, the framework that has worked beautifully for decades, has a hole in it, not a small one, a 2 billion light-year hole. The technical term for this kind of problem is a selection effect. If you're trying to measure the properties of the universe but you happen to be sitting in an unusual location, your measurements will reflect that location rather than the universe at large. Imagine trying to measure the average temperature of a city, but your thermometer is sitting inside a walk-in freezer. You'd conclude the city is much colder than it actually is, not because your thermometer is broken, but because you're sampling from the wrong place. The KBC Void raised the possibility that every measurement we make of the local universe, the Hubble constant, the density of matter, the rate of structure formation, might be distorted by the fact that we're sitting in a cosmic freezer. A region where the density is low, the gravity is weak, and space expands a little faster than it does in the denser parts of the universe. That possibility had been floated before, quietly, by a handful of researchers who had noticed the local underdensity in earlier surveys and wondered whether it might explain the Hubble tension. But those papers hadn't gained much traction because the underdensity they were describing was modest. A 10 or 15% dip in density over a few 100 million light-years. Annoying maybe, but not large enough to explain a 9% discrepancy in the Hubble constant. The KBC Void was different. A 20 to 50% deficit over a billion light-years was large enough to matter. It was large enough to shift local measurements of cosmic expansion by several percent, possibly more, depending on exactly how the density varied with distance and how the void's gravity, or lack of it, affected the motion of galaxies. Some researchers immediately started running simulations to see if a void that size could account for the Hubble tension. The math was tricky. You couldn't just subtract 20% from the local density and assume everything else stayed the same. The presence of a giant underdensity changes the gravitational landscape. Galaxies near the center of a void feel less inward pull from surrounding matter, so they drift outward faster than they would in an average environment. That faster drift shows up as a higher apparent recession velocity when you measure their redshifts. If you're using those galaxies as distance markers to calculate the Hubble constant, your result comes out high. Not because the universe is expanding faster everywhere, but because you're measuring a local effect and mistaking it for a global one. The simulations gave mixed results. Some models suggested the KBC Void could explain about half the Hubble tension, bringing the local measurement down from 73 to somewhere around 70, which was closer to the cosmic microwave background value of 67, but still not a perfect match. Other models were less optimistic, showing that even a void this large couldn't fully account for the discrepancy unless the density gradient was steeper than the observations suggested. The debate continues. What everyone agreed on, though, was that the void mattered. It wasn't just a geographic curiosity. It was a systematic bias sitting in the middle of our data, and ignoring it would lead to wrong conclusions about the universe at large. One of the strange things about the KBC Void is how long it took to find. The data had been sitting there for years. Galaxy surveys in the 1990s and early 2000s had already mapped much of the local universe. The underdensity was visible in those maps if you knew where to look. But nobody looked because nobody expected to find something that large. The human brain is very good at seeing patterns. It's also very good at dismissing patterns that don't fit expectations. If the standard model says voids larger than a few 100 million light-years should be vanishingly rare, and you see a hint of something bigger in your data, the natural reaction is to assume you made a mistake. Maybe the survey missed some galaxies. Maybe the statistical analysis was off. Maybe the signal is noise. It takes a certain kind of stubbornness to look at that signal and decide it's real, even when the theory says it shouldn't be. Keenan, Barger, and Cowie had that stubbornness. Part of it came from the way they built their dataset. By combining multiple surveys, each with different systematic errors and selection effects, they could cross-check the results. If the underdensity showed up in optical data but not in infrared, or in X-ray but not in radio, that would suggest the signal was an artifact of one particular instrument or method, but it showed up everywhere, in every wavelength, in every survey. The galaxies were missing, and the missing galaxies were consistent across independent measurements. That consistency is what gave the team confidence to publish, and once the paper came out, other researchers started re-examining their own datasets and finding the same thing. The void had been hiding in plain sight. There was also a technological component. Earlier surveys had been limited by the sensitivity of their detectors and the time available on telescopes. Faint galaxies at large distances were hard to spot, which meant density measurements at the edge of the void were noisy. By the early 2010s, detector technology had improved. Cameras on telescopes could see fainter objects, spectrographs could measure redshifts more accurately, and crucially, astronomers had access to huge archives of existing data that could be reprocessed with better algorithms. Keenan's team didn't need to go out and observe new galaxies, they just needed to look at the old data more carefully. That's a recurring theme in astronomy. Sometimes the breakthrough isn't a bigger telescope, it's a better question. The void's scale was hard to visualize. 2 billion light-years is not a distance the human brain has any intuition for. Light itself, the fastest thing in the universe, takes 2 billion years to cross it. If you stood at one edge of the KBC Void and pointed a flashlight toward the other side, the photons leaving your flashlight would arrive at their destination long after the sun had died, long after the Earth had been consumed, long after any planet in our solar system bore any resemblance to what it looks like today. Galaxies at the far edge of the void are so distant that we see them as they existed 2 billion years ago. Since then, those galaxies have aged, stars have been born and died, planets have formed, entire civilizations could have risen and fallen, and the light carrying that information is still on its way, crawling across the emptiness at 300,000 kilometers per second. And yet, despite the scale, the void is not empty. This is important. When astronomers say a region is underdense, they don't mean it contains nothing, they mean it contains less than average. The KBC Void still has galaxies, thousands of them. Millions probably if you count the small ones. It still has dark matter, the invisible scaffolding that makes up most of the mass in the universe. It still has gas, thin clouds of hydrogen and helium drifting through intergalactic space. What it doesn't have is the usual concentration of those things. Imagine a crowded room where people are packed shoulder to shoulder. Now imagine the same room with half the people. It's still occupied. It's just noticeably less dense. That's the void, a place where the universe decided not to put as much stuff. The geometry matters too. The void isn't a perfect sphere. Cosmic structures never are, but it's roughly spherical, which is unusual. Most voids in the cosmic web are elongated, stretched along filaments, or flattened into pancakes by the gravitational pull of surrounding clusters. The KBC Void's near-spherical shape suggests it formed differently, possibly very early in the universe's history when matter was still relatively smooth and hadn't yet been sculpted into the web of filaments we see today. Some models propose that regions like the KBC Void are relics of quantum fluctuations in the first moments after the Big Bang. Tiny underdense patches that expanded along with the universe, growing larger over time but never attracting enough matter to fill in. If that's true, the void we're sitting in is older than most galaxies. It's been here, quietly underoccupied, since the cosmos was young. One researcher who took the KBC Void seriously almost immediately was Indranil Banik, a postdoctoral astronomer at the University of Bonn in Germany. Banik had been studying anomalies in galaxy rotation curves and gravitational dynamics, and he was already suspicious that something about the local universe wasn't matching the standard model. When the KBC Void paper came out, he saw it as a potential explanation for several puzzles at once. In 2020, Banik published a detailed analysis arguing that the void could help resolve not just the Hubble tension, but also discrepancies in measurements of the matter density and the clumpiness of structure on large scales. His paper made a bold claim. He calculated that under the standard model, a void as large and as underdense as the KBC Void was a 10 sigma event. 10 sigma. For context, in particle physics, a 5 sigma result is considered the gold standard for declaring a discovery. It means the probability of the signal being a random fluke is less than 1 in 3.5 million. A 10 sigma event is so statistically improbable that the odds of it happening by chance are essentially zero. 1 in many trillions. If Banach's calculation was correct, and the Standard Model really did predict that the KBC Void should not exist, then either we were living in the single most unlikely place in the observable universe, or the Standard Model was wrong. Banach leaned toward the second option. He argued that the void's existence was evidence that the assumptions underpinning modern cosmology, specifically the cosmological principle and the way structure forms in a dark matter-dominated universe, needed to be revisited. Not everyone agreed with Banach's interpretation. Some cosmologists pointed out that calculating the probability of a rare event depends heavily on your assumptions about how structure forms, and those assumptions have uncertainties. Maybe the Standard Model's predictions weren't as rigid as Banach thought. Maybe voids this large were rare but not impossible. Maybe we just got unlucky. The debate is ongoing. What's not debatable is the void itself. It's there. The galaxy counts are lower. The density is down. The structure extends for 1 billion light-years in every direction. Whether that structure is a fatal blow to the cosmological principle or just an unusually large but still permissible fluctuation is a question that depends on which cosmologist you ask and what assumptions they're willing to bend. By the mid-2010s, the KBC Void had moved from controversial to acknowledged. It appeared in textbooks. It showed up in conference talks. Researchers planning future galaxy surveys made sure their observing programs would cover the void's boundaries so they could map the transition from underdense to average and test whether the density gradient matched predictions. The void had become part of the landscape, a known feature of the local universe. And with that acknowledgement came a shift in how cosmologists thought about their measurements. If we're sitting in a hole, then every local observation carries an asterisk. The Hubble constant we measure might not be the Hubble constant everywhere else. The rate at which galaxies are forming stars in our neighborhood might not match the rate in denser regions. The way dark matter clumps and clusters nearby might not reflect the way it behaves across the universe at large. We weren't looking at the cosmos from a neutral vantage point. We were looking at it from inside an anomaly. That realization didn't overturn cosmology. The Standard Model still works beautifully on average. Zoom out far enough, past the void, past the superclusters, past the largest filaments, and the universe does smooth out. The cosmic microwave background, our view of the universe at its largest and earliest scales, is uniform to 1 part in 100,000. The predictions of the Standard Model still match that uniformity. What the KBC Void does is add a layer of complexity. It means we can't assume our local measurements are representative of the whole. It means we have to correct for our location the way a surveyor corrects for the curvature of the Earth. And it means the universe is weirder than we thought. Not because it breaks the rules, but because the rules allow for structures so large that even a galaxy full of intelligent life could spend centuries mapping the cosmos and never realize they were sitting inside one. The void also raised a philosophical question that most scientists prefer not to talk about in polite company. If the largest structure we've ever found happens to be centered on us, what does that say about the Copernican principle, the idea that we don't occupy a special place in the universe? For 500 years, astronomy has been in the business of decentering humanity. We're not at the center of the solar system. We're not at the center of the galaxy. We're not in a special galaxy in a special part of the universe. We're average, typical, unremarkable. The KBC Void complicates that story. We're not at the center of the universe, but we are near the center of the largest known underdensity. That's not special in a flattering way. It's special in the way being the only person in a nearly empty subway car at 3 in the morning is special. You're not important, you're just alone. And the fact that we happen to be here, in the quietest part of the cosmic web, Asking questions about why the universe looks the way it does is either a coincidence so unlikely it borders on suspicious, or a clue that we're missing something fundamental about how structure forms and how observers end up where they do. Either way, the KBC Void had shifted the ground beneath cosmology. What started as a measurement problem, a small discrepancy in galaxy counts, had turned into something much larger, a 2 billion light-year question mark sitting in the middle of our data. And the strange thing was, now that we knew it was there, we couldn't unsee it. Every new survey, every new telescope, every new map of the local universe confirmed it. The void was real. We were inside it. And whatever that meant for our understanding of the cosmos, we were about to find out. The thing about the KBC Void that makes it genuinely unsettling is not the size, though the size is absurd. It's not even the fact that we're sitting near the middle of it, though that raises questions nobody has good answers for. What makes it unsettling is what happens when you zoom in and start asking what the void actually is, because it turns out the void is not empty, it's full. Full of galaxies, full of stars, full of dark matter, full of gas. It's just less full than it should be. 20 to 50% less full depending on where you measure. And that deficit, that missing matter, changes everything about how physics works inside it. To understand why that matters, you need to understand what holds the universe together in the first place. Not gravity in the way you learnt it in high school, though gravity is part of it. What holds the cosmic web together, what keeps galaxies clustered along filaments and prevents everything from flying apart into a featureless mist, is dark matter. And dark matter is one of the most frustrating concepts in modern physics because we know it's there and we have no idea what it is. Here's what we do know. In the 1930s, an astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma cluster. He measured how fast individual galaxies were moving within the cluster by looking at their Doppler shifts. The galaxies were moving fast, too fast. When Zwicky added up all the visible matter in the cluster, all the stars and gas he could detect, and calculated how much gravity that matter should produce, the answer was nowhere near enough to keep the galaxies from flying apart. The galaxies were moving at speeds that should have let them escape the cluster's gravity well entirely. But they weren't escaping. They were staying put, orbiting each other in a stable configuration. The only explanation was that there was more matter in the cluster than he could see, a lot more. Zwicky called it dark matter, and for decades most astronomers ignored him because the idea sounded ridiculous. Then in the 1970s, Vera Rubin measured the rotation curves of spiral galaxies. A rotation curve tells you how fast stars are moving at different distances from a galaxy's center. In a normal galaxy, if most of the mass is concentrated in the bright core, stars farther out should move slower, the same way planets farther from the Sun orbit more slowly than planets closer in. That's how Kepler's laws work. That's how gravity works. Rubin's measurements didn't follow the script. Stars at the outer edges of galaxies were moving just as fast as stars near the center, sometimes faster. The only way that made sense was if the galaxy was embedded in a giant halo of invisible matter extending far beyond the visible disk. The halo had to be massive, at least 5 or 6 times more massive than all the stars and gas combined. And it had to be invisible because telescopes couldn't see it at any wavelength. By the 1980s, the evidence was overwhelming. Galaxies had dark matter halos. Galaxy clusters had even larger halos. Gravitational lensing, the way light bends around massive objects, showed dark matter distributed across the universe in enormous web-like structures. Simulations of how galaxies form only worked if you included dark matter. Take it out and the simulations fell apart. Galaxies didn't form. Clusters didn't form. The cosmic web didn't exist. Dark matter wasn't optional. It was load-bearing. We still don't know what it's made of. The leading theory is that it's some kind of particle that doesn't interact with light or normal matter, except through gravity. Something that passes through ordinary atoms like a ghost, never colliding, never emitting radiation, just pulling on things with its mass. Physicists have built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to smash into an atomic nucleus and register a signal. After decades of searching, they've found nothing. Other experiments have looked for dark matter particles annihilating each other in the cores of galaxies, producing gamma rays or other high-energy radiation. Nothing. Dark matter remains invisible, undetectable except through its gravitational effects. It's the most abundant form of matter in the universe, and we can't touch it. What we can do is map it, not directly, but by measuring how it bends space. Light traveling through the universe follows the curvature of spacetime, and massive objects curve spacetime around them. If you look at a distant galaxy and see its image distorted, stretched into an arc, or split into multiple images, that's a sign that something massive is sitting between you and that galaxy, bending the light on its way to your telescope. Often that something is a galaxy cluster. But the amount of bending doesn't match the amount of visible matter in the cluster. The missing mass, the stuff doing most of the bending, is dark matter. By mapping these distortions across large areas of sky, astronomers can reconstruct where the dark matter is. And what those maps show is that dark matter isn't spread evenly. It clumps into halos around galaxies, threads along filaments connecting galaxy clusters, and forms enormous web-like structures spanning hundreds of millions of light-years. Where dark matter goes, visible matter follows. The dark matter provides the gravity well, and ordinary matter falls into it. Now here's where the KBC Void gets interesting. Dark matter is still there. The void is not empty of dark matter. But there's less of it, a lot less. Current estimates put the dark matter density in the KBC Void at somewhere around 15 to 20% of the cosmic average. That's a huge deficit, and it changes the gravitational landscape in a way that ripples through every physical process happening inside the void. Gravity, at its core, is an attractive force. It pulls things together. In a typical region of the universe, the density of matter is high enough that gravity is the dominant player on large scales. It's constantly pulling galaxies toward each other, slowing their expansion, clustering them into groups and filaments. But gravity's strength depends on how much matter is nearby. In a dense region, gravity is strong. In an underdense region, it's weak. And when gravity gets weak enough, another force starts to dominate: dark energy. Dark energy is even stranger than dark matter because it doesn't clump, it doesn't form halos, and it doesn't weaken over distance. It's a property of space itself, a kind of pressure that pushes outward, making the universe expand faster over time. In regions where matter is abundant, gravity wins the tug of war and dark energy's effects are negligible. But in voids where matter is sparse, dark energy takes over. The expansion of space accelerates. Galaxies drift apart faster than they would in a denser region. And if you're sitting in a void trying to measure how fast the universe is expanding by watching nearby galaxies, you're going to get a number that's higher than the true cosmic average, not because the universe is expanding faster everywhere, but because your local patch of space is expanding faster than average and you don't realize it. This is the crux of the void model, a hypothesis that's been gaining traction since the KBC Void was confirmed. The void model says that the Milky Way is sitting in a region where gravity is weaker than average, where dark energy is more dominant than average, and where space is expanding faster than average. If that's true, then every measurement we make of the local expansion rate, every supernova we use as a distance marker, every galaxy whose redshift we measure is giving us a biased answer. We're measuring the expansion rate of the void, not the expansion rate of the universe. And the difference between those two numbers might explain why the Hubble constant measured locally doesn't match the Hubble constant predicted by the cosmic microwave background. Let's walk through what that means in practice. Imagine you're an astronomer in the early 21st century. You want to measure the Hubble constant, the rate at which the universe is expanding right now. The method you use involves finding a specific type of exploding star called a Type 1a supernova. These supernovae are useful because they all explode with roughly the same peak brightness. Measure how bright one looks from Earth, compare it to how bright it should be intrinsically, and you can calculate how far away it is. Measure the supernova's redshift, which tells you how fast it's moving away, and you can calculate the Hubble constant. Distance divided by velocity equals expansion rate. Here's the problem. The supernovae you're measuring are not sitting in average regions of the universe. Many of them are within a few 100 million light-years of the Milky Way, which means they're inside the KBC Void or close to its edge. And inside the void, space is expanding faster than it does in denser regions. So when you measure the supernova's redshift, you're measuring a velocity that's been boosted by the void's accelerated expansion. When you calculate the Hubble constant from that measurement, the number comes out high. Not because your instruments are bad, not because the supernova is weird, but because you're measuring a local effect and assuming it's global. Now imagine a different method. Instead of measuring supernovae, you look at the cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old. The microwave background is uniform to 1 part in 100,000, with tiny temperature fluctuations that encode information about the conditions in the early universe. By analyzing those fluctuations, you can measure the density of matter, the density of dark energy, and the rate at which the universe was expanding back then. Plug those numbers into the standard model of cosmology, run the equations forward 13.8 billion years, and you get a prediction for how fast the universe should be expanding today. That prediction comes out around 67 kilometers per second per megaparsec. Two methods, same universe, different answers. 73 from supernovae, 67 from the microwave background. The gap is 9%, and it's been stable for more than a decade, despite increasingly precise measurements on both sides. The void model offers a resolution. The microwave background gives you the true cosmic expansion rate because it's averaging over the entire observable universe. The supernova method gives you the local expansion rate because you're sitting in a void. Correct for the void's faster expansion, and the two numbers should converge. That's the theory anyway. Whether it actually works depends on the details. How much faster is space expanding inside the void compared to outside? How does the density gradient change as you move from the center of the void toward its edge? How does the void's gravity, or lack of it, affect the motion of galaxies at different distances? These are hard questions, and answering them requires detailed simulations that model how matter behaves in underdense regions over billions of years. Several research groups have been running those simulations since the void was confirmed, and the results are mixed. Some models suggest the void can account for about half the Hubble tension. Others say it's not quite enough. None of them say it's irrelevant. One of the clearest studies came out in 2020 in the journal Monthly Notices of the Royal Astronomical Society. Benjamin Hochheit, a researcher at the University of Wisconsin-Madison, led a team that combined galaxy survey data with simulations of void expansion. They found that the density deficit in the KBC void was consistent with a local expansion rate that was several percent higher than the cosmic average. The exact number depended on how you modeled the dark matter distribution and how you accounted for the peculiar velocities of galaxies, but the effect was there. Hoshate's paper included a quote that got picked up by science journalists and turned into headlines. The Hubble constant is higher using the supernova method, in accordance with how we would expect a void to affect the Hubble constant. That phrasing is careful, in accordance with how we would expect. Not proof, not confirmation, just consistency. The void model predicts a higher local Hubble constant, and the local measurements are higher. That doesn't mean the void is the only explanation, but it does mean the void is a viable explanation. And in a field where the Hubble tension has been called a crisis, viable explanations are worth taking seriously. The void model also makes other predictions that can be tested. If the KBC void is accelerating the local expansion rate, then galaxies at the edge of the void should be moving faster relative to us than galaxies outside the void. That motion should show up in peculiar velocity surveys, which measure how galaxies deviate from the smooth Hubble flow. Several teams are working on those surveys now, mapping the velocities of thousands of galaxies out to distances that span the void's boundary. If the void model is correct, they should see a transition zone where velocities shift as you move from the underdense interior to the denser regions beyond. That transition hasn't been conclusively detected yet, but the data is noisy and the measurements are hard. It might take another decade of observations to settle the question. There's another wrinkle. The void is not a perfect vacuum. It contains galaxies, thousands of them, millions probably if you count the small dim ones that are hard to detect. And those galaxies are not distributed randomly. They're clustered into groups and filaments, just like galaxies everywhere else. The difference is that the filaments are thinner and the clusters are smaller. The web is there, but it's sparse. Think of the cosmic web as a sponge. In a dense region, the sponge is tightly packed with small pores and thick walls. In a void, the sponge is stretched out with large pores and thin walls. The structure is the same. The scale is different. That structure matters because it affects how galaxies move. In a dense region, galaxies are constantly being tugged by the gravity of nearby clusters. Their motion is complicated, influenced by dozens of gravitational sources pulling in different directions. In a void, the pulls are weaker and farther apart. Galaxies drift more freely. Their peculiar velocities, the deviations from the Hubble flow, are smaller. And because those velocities are smaller, it's easier to measure the underlying expansion of space. In principle, that makes voids ideal laboratories for cosmology. You can see the expansion more clearly because there's less gravitational noise. The KBC void should be an astronomer's dream, a natural laboratory sitting right in our backyard where the effects of cosmic expansion are easier to isolate. Instead, it's a headache because the expansion we're measuring in our backyard might not match the expansion happening everywhere else. The void structure also raises questions about how it formed in the first place. Voids are not unusual. The universe is full of them. But most voids are a few 100 million light-years across. The KBC void is 2 billion light-years across, 7 times larger than average. Structures that large are supposed to be rare. According to simulations based on the standard model, a void this size should occur less than once per observable universe. The fact that we're sitting in one is either an extraordinary coincidence or a sign that the standard model is missing something. One possibility is that the void formed early, very early, in the first few 100 million years after the Big Bang, when matter was still relatively smooth and hadn't yet clumped into the cosmic web. Tiny underdense regions in the early universe, Quantum fluctuations from the inflationary era could have expanded along with space, growing larger over billions of years but never attracting enough matter to fill in. If the KBC Void is one of those primordial underdensities, then it's older than most galaxies. It's been here, quietly underoccupied, since the cosmos was young. That would explain why it's so large. It had more time to grow. It also means the void is a fossil, a relic of the universe's infancy preserved in the distribution of galaxies today. Another possibility is that the Standard Model underestimates how efficiently matter drains out of voids and into filaments. The simulations that predict void sizes assume a certain rate of gravitational collapse, a certain efficiency with which dark matter halos pull in surrounding gas and turn it into galaxies. If that efficiency is higher than the models assume, then voids would grow larger and emptier than predicted. The KBC Void would still be unusual, but not impossible. This is an active area of research. Cosmologists are rerunning their simulations with different assumptions about dark matter, about how galaxies form, about how gas cools and collapses. Some of those simulations produce voids as large as the KBC Void. Others don't. The jury is still out. What's not in question is the void's impact on the local gravitational environment. Gravity inside the KBC Void is weaker than average. Not by a lot, but measurably. If you could somehow stand outside the universe and watch galaxies moving through the void, you'd see them drifting apart more slowly than galaxies in a dense region. Not because space is expanding faster inside the void, although it is, but because there's less matter pulling them back together. In a dense region, gravity fights expansion. In a void, gravity gives up. Dark energy wins by default. That shift in the balance between gravity and dark energy has implications beyond the Hubble constant. It affects how galaxies form stars. Star formation depends on gas collapsing under gravity. In a dense region where gravity is strong, gas clouds collapse faster and form stars more efficiently. In a void where gravity is weak, gas clouds take longer to collapse. Star formation rates are lower. Galaxies grow more slowly. The Milky Way itself, sitting in the middle of the KBC Void, might have formed stars at a different rate than galaxies in denser regions. Not dramatically different, but enough that if you compared our galaxy's history to the history of a similar galaxy in a supercluster, you'd see discrepancies. Some researchers have even suggested that the void might explain other local anomalies. The fact that the local group, the collection of galaxies that includes the Milky Way and Andromeda, is moving at about 600 kilometers per second relative to the cosmic microwave background in a direction that doesn't align neatly with any obvious gravitational source. The fact that the distribution of satellite galaxies around the Milky Way is lopsided, with more satellites on one side than the other. The fact that certain measurements of the matter density in the local universe don't match the predictions from the microwave background. None of these anomalies are individually convincing, but taken together, they suggest the local universe is messier than the Standard Model predicts. And the KBC Void, with its reduced gravity and accelerated expansion, might be the unifying explanation. The void also complicates our understanding of what average means. For decades, cosmologists have assumed that if you pick a random spot in the universe and measure the local density, you'll get something close to the cosmic mean. Sure, you might land in a void or a filament, but those features are small enough that they average out over large volumes. The KBC Void breaks that assumption. If you're sitting in a 2 billion light-year underdensity, your local measurements are not close to the cosmic mean, they're systematically biased, and if you don't know you're in a void, you'll draw the wrong conclusions about what the universe looks like elsewhere. This is not a new problem. Astronomers have known for a long time that local measurements can be biased by large-scale structure. But the size of the KBC Void makes the bias larger than anyone expected. It's one thing to correct for a 300 million light-year void. It's another thing to correct for a 2 billion light-year void. The math gets harder, the uncertainties grow, and suddenly measurements that seemed rock solid start looking shaky. The strangest part is that the void is not hostile to life. It's not a cosmic wasteland where galaxies are dying and stars refuse to form. It's just quieter, less crowded. The Milky Way formed here, planets formed here, life formed here. Whatever disadvantages the void imposes, they're subtle enough that intelligent observers can still evolve and look up at the sky and ask questions about what they're seeing. But the answers to those questions are shaped by the fact that we're asking them from inside a deficit, a place where the universe has less stuff than it should. And every measurement we make, every conclusion we draw, carries that deficit forward. We're mapping the cosmos from the bottom of a gravitational dip, and until very recently, we didn't know the dip was there. Now we come to the part where the void stops being a geographic curiosity and turns into a genuine problem for cosmology, because it turns out that sitting inside a 2 billion light-year underdensity doesn't just change where you are, it changes what you see. Specifically, it changes how fast you think the universe is expanding. And for the last 15 years, that measurement, the single number that's supposed to tell us the rate at which space itself is stretching apart, has been tearing the field of cosmology in half. The number is called the Hubble constant, named after Edwin Hubble, the astronomer who in 1929 discovered that distant galaxies are moving away from us and that the farther away they are, the faster they're receding. That relationship, distance equals velocity divided by the Hubble constant, became the foundation of modern cosmology. It told us the universe is expanding. It gave us a way to measure that expansion. And for nearly a century, astronomers have been trying to pin down the exact value of that constant with increasing precision. The goal was simple: measure it well enough, and you'd know the age of the universe, the size of the observable cosmos, and the fate of everything that exists. One number: extraordinary consequences. By the early 2000s, the Hubble constant had converged. Multiple independent teams using different methods were all getting values around 70 kilometers per second per megaparsec. That's astronomer shorthand for saying that for every 3.26 million light-years you look outward, galaxies are moving away from you 70 kilometers per second faster. The measurement had a small margin of error, a few percent at most, and everyone agreed the problem was solved. We knew how fast the universe was expanding. We could move on to other questions, except the problem wasn't solved. It was about to split wide open. In 2013, the European Space Agency's Planck satellite released its final measurements of the cosmic microwave background, the faint afterglow of radiation left over from when the universe was 380,000 years old. Planck had spent years mapping the temperature fluctuations in that glow with exquisite precision, and from those fluctuations, physicists could extract the conditions of the early universe, the density of matter, the density of dark energy, the curvature of space, all of it encoded in a pattern of hot and cold spots spread across the sky. By plugging those conditions into the equations of general relativity and running the clock forward 13.8 billion years, the Planck team could predict what the Hubble constant should be today. The answer they got was 67 kilometers per second per megaparsec, clean number. Tiny error bars, high confidence, and it didn't match the local measurements, not even close. At the same time, a team led by Adam Rees at Johns Hopkins University, the same Adam Rees who won a Nobel Prize for discovering that the universe's expansion is accelerating, was measuring the Hubble constant using a completely different method. Rees and his colleagues, working under a collaboration called SH0ES, were using supernovae as distance markers, type 1a supernovae to be specific. These are exploding white dwarf stars, and they're useful because they all explode with roughly the same peak brightness. Spot one in a distant galaxy, measure how bright it looks from Earth, compare that to how bright it should be intrinsically, and you've got a distance. Measure the galaxy's redshift, which tells you how fast it's moving away, and you've got the Hubble constant. The SH0ES team had been refining this method for years, using the Hubble Space Telescope to observe hundreds of supernovae across billions of light years. By 2019, they had measured the Hubble constant to within 1% uncertainty. The value they got was 73 kilometers per second per megaparsec, not 67, 73, a difference of 9%. In a field where measurements are routinely precise to fractions of a percent, 9% is not a rounding error, it's a chasm. Two methods, same universe, same physical laws, different answers. One method looks backward, using the cosmic microwave background to infer what the expansion rate should be based on conditions in the infant universe. The other method looks around, measuring distances and velocities of objects in the nearby cosmos. Both methods are grounded in solid physics. Both teams checked and rechecked their data, and the gap between 67 and 73 refused to close. By the late 2010s, the discrepancy had a name, the Hubble Tension, and it had become one of the biggest unsolved problems in cosmology. The tension matters because it's not just about a number, it's about whether we understand how the universe works. If the Planck measurement is correct, then the local measurements are wrong, and something is biasing our observations of nearby galaxies. If the local measurements are correct, then the Planck prediction is wrong, which means either our model of the early universe is incomplete, or the physics governing cosmic expansion has changed in ways we haven't accounted for. Either way, something is broken, and for a field that prides itself on precision, broken is not a comfortable place to be. At first, the assumption was that someone had made a mistake. Measuring distances in astronomy is hard. It relies on a technique called the cosmic distance ladder, a series of steps where each rung depends on the accuracy of the rung below it. You start with nearby stars whose distances you can measure directly using parallax, the apparent shift in a star's position as Earth moves around the Sun. From there, you step outward to a class of pulsating stars called Cepheid variables. These stars brighten and dim at a rate directly tied to their intrinsic luminosity. Measure the pulse, calculate the true brightness, compare it to how bright the star looks, and you've got a distance. Cepheids can be seen out to about 100 million light-years, which gets you into galaxies far enough away that you can start spotting type 1a supernovae. Once you've calibrated the supernovae using galaxies that contain both Cepheids and supernovae, you can use the supernovae alone to reach out billions of light-years. The method works. It's been tested and validated over decades. But each step introduces uncertainties, and those uncertainties add up. Critics of the local measurement argued that something in the distance ladder was off. Maybe the Cepheids were blended with other stars, making them appear brighter than they really were. Maybe dust was dimming the light in ways the corrections weren't fully accounting for. Maybe the supernovae themselves weren't as uniform as everyone thought. So Rees pointed the James Webb Space Telescope at the same stars. Webb, with its 6.5-meter mirror and infrared sensitivity, could cut through dust and crowding with a precision Hubble never had. If blending was the problem, Webb would see it. The Cepheids would look dimmer through Webb's eyes, the distances would stretch, and the Hubble constant would drop back towards 67. Crisis averted. That is not what happened. Webb confirmed the measurements. The Cepheids looked the same, the distances held, the Hubble constant stayed at 73. By 2024, after multiple observations with Webb covering galaxies out to 130 million light-years, Rees and his team were confident enough to publish a definitive statement. Measurement error could be ruled out with very high confidence. That left two possibilities. Either the cosmic microwave background measurement was wrong, which seemed unlikely given how well Planck's results matched other predictions of the Standard Model, or something about the local universe was different from the universe at large. And that's where the KBC Void enters the picture. The Void model, as it's come to be called, offers a surprisingly elegant resolution to the Hubble tension. The key insight is that the expansion rate of space is not the same everywhere. In dense regions of the universe, where galaxies are packed into clusters and filaments, gravity is strong. That gravity slows the expansion. Galaxies are being pulled back toward each other even as space itself tries to stretch them apart. In underdense regions, in voids, gravity is weak. Dark energy, the mysterious force driving the universe's accelerated expansion, takes over. Space expands faster in voids than it does in dense regions. Not by a huge amount, but measurably. If the Milky Way is sitting in the middle of a 2 billion light-year void, then every measurement we make of the local expansion rate is biased. We're not measuring the expansion rate of the universe, we're measuring the expansion rate of the void. And because the void is expanding faster than average, our measurements come out high, 73 instead of 67. The cosmic microwave background gives you the true cosmic expansion rate because it's averaging over the entire observable universe, smoothing out the voids and the clusters and the filaments into a single mean value. The supernova method gives you the local rate because the supernovae you're measuring are close enough that many of them are inside the void or near its boundary. Correct for the void's faster expansion, and the two numbers should converge. That's the theory. Whether it works in practice depends on the details, and this is where things get technical. The effect of a void on local expansion measurements depends on three things: how underdense the void is, how large it is, and where you're sitting inside it. The more underdense the void, the faster space expands within it. The larger the void, the more galaxies you observe that are affected by its accelerated expansion. And if you're sitting near the center of the void, as the Milky Way appears to be, then the bias is maximized because you're surrounded in all directions by underdense space. In 2020, a researcher named Indranil Banik at the University of Bonn in Germany published a detailed analysis in the journal Monthly Notices of the Royal Astronomical Society that put numbers to this idea. Banik took the measured properties of the KBC void, its size, its density deficit, its roughly spherical shape, and ran simulations to calculate how much the void would inflate local measurements of the Hubble constant. His conclusion was striking. A void with the KBC void's properties could cause the local Hubble constant to appear about 11% higher than the true cosmic value. 11%. The actual discrepancy between the Planck and SH0 ES measurements is 9%. The void model doesn't just point in the right direction, it overshoots slightly, which means either the void's properties are slightly different from what we've measured, or there are other factors moderating the effect. But the fact that the numbers are in the same ballpark is remarkable. Banik's paper included a line that got picked up by journalists and turned into headlines. The Hubble tension is largely a local phenomenon. By that, he meant the discrepancy isn't a sign that the laws of physics are different in different parts of the universe, or that dark energy is evolving in unexpected ways. It's a sign that we're sitting in an unusual location, and our measurements reflect that location rather than the cosmos at large. A local solution like a local void is a promising way to go about solving the problem. That phrasing, local solution, is important because it sidesteps the need for exotic new physics. You don't have to rewrite the textbooks or invoke particles that don't exist. You just have to account for the fact that we're sitting in a hole. The mechanism behind the effect is sometimes called the Hubble bubble, and it's worth understanding because it's counterintuitive. You'd think that if you're in a void where the density is low, galaxies would be moving away from you more slowly because there's less gravity pulling them around, but the opposite is true. Inside a void, galaxies near the center drift outward toward the denser walls because that's where the mass is. If you're sitting near the center of the void, you see galaxies in all directions moving away from you faster than they would in an average environment. Not because space is expanding faster everywhere, though it is expanding faster locally, but because the galaxies are being pulled outward by the gravity of the matter outside the void. That outward drift adds to their recession velocity. When you measure their redshifts and calculate the Hubble constant, you get a number that's inflated by the void's influence. Think of it like standing in the middle of a shallow depression on a hillside. If you roll a ball in any direction, it's going to pick up a little extra speed as it rolls down the slope toward the denser ground outside the depression. The ball's motion doesn't just reflect how steep the hill is overall, it reflects the local slope you're sitting on. The same thing happens with galaxies in a void. Their motion doesn't just reflect the cosmic expansion rate, it reflects the local gravitational landscape, which is tilted outward because you're in an underdense region. Banach wasn't the first to propose this idea, but his paper was the most detailed. Earlier work by Benjamin Hochet and collaborators at the University of Wisconsin-Madison in 2020 had already shown that the KBC void was consistent with a higher local Hubble constant. Hochet's team used galaxy survey data combined with simulations of void dynamics to show that the density gradient in the void could account for several % of the Hubble tension. They were careful not to claim the void explained the entire discrepancy, but they noted that the effect was in the right direction and the right magnitude to be significant. The void model gained traction quickly because it explained not just the Hubble tension, but other local anomalies that had been piling up. The peculiar velocities of galaxies in the local universe, the flows of matter that didn't seem to match the distribution of visible mass, the cold spot in the cosmic microwave background, which some researchers had already proposed might be linked to a supervoid. The fact that certain measurements of the matter density in the local universe, based on galaxy counts and gravitational lensing, were coming in slightly lower than the cosmic average, all of these could be symptoms of the same underlying cause. We're in a void. The void changes the gravitational environment, and that changed environment shows up in every measurement we make that's sensitive to local structure. Of course, not everyone was convinced. Some cosmologists argued that the void model was too convenient, a just-so story that explained the data by invoking a feature we happened to be sitting in. The Copernican principle, the idea that we don't occupy a special place in the universe, has been a guiding assumption in cosmology for centuries. Finding ourselves near the center of the largest known void in the universe felt like a violation of that principle. Sure, somebody had to be sitting in the void, but why us? Why now, at the exact moment in history when we're capable of measuring the Hubble constant with enough precision to notice the discrepancy? The odds felt suspicious. Banach addressed this directly in his paper. He calculated the statistical probability of the KBC void existing under the standard model of cosmology. His answer was that the void was a 10 sigma event. 10 sigma. In particle physics, a 5 sigma result is the threshold for declaring a discovery. It means the probability of the signal being a random fluke is less than 1 in 3.5 million. A 10 sigma event is so statistically improbable that the odds of it happening by chance are essentially zero. one in many trillions. If Banach's calculation was correct, then either we're living in the most unlikely place in the observable universe, a coincidence so extreme it borders on suspicious, or the Standard Model's predictions about how large voids can grow are wrong. Banach leaned toward the second option. He argued that the existence of the KBC Void was evidence that the assumptions underpinning structure formation in a dark matter-dominated universe needed to be revisited. Maybe voids can grow larger than simulations predict. Maybe the efficiency with which matter drains out of underdense regions and into filaments is higher than the models assume. Maybe there's something about the early universe, some feature of the initial density fluctuations that allowed a handful of enormous voids to form even though they're rare. Any of those possibilities would relax the statistical tension. The void would still be unusual, but not impossible. Other researchers pushed back on Banach's 10 sigma claim. They pointed out that calculating the probability of a rare structure depends heavily on your assumptions about how the universe forms that structure, and those assumptions have uncertainties. The simulations that predict void sizes are based on models of dark matter clustering, galaxy formation, and gas dynamics, all of which have free parameters that aren't perfectly constrained. Tweak those parameters within their allowed ranges, and the predicted void sizes change. Maybe the KBC Void is a 3 sigma event instead of 10 sigma, still rare but not unimaginably rare. The debate over how statistically unlikely the void is continues, but what's not debatable is that it exists and it's large. There are alternative explanations for the Hubble tension that don't involve the void. Some physicists have proposed that dark energy, the mysterious force driving the universe's accelerated expansion, is not constant but evolves over time. If dark energy was weaker in the early universe and has been growing stronger, that would cause the expansion rate to increase faster than the Standard Model predicts. The cosmic microwave background would give you the expansion rate from when dark energy was weaker, and local measurements would give you the rate now when dark energy is stronger. The gap between the two would reflect the evolution of dark energy, not a local bias. Another idea is that there's an extra form of radiation in the early universe that we haven't accounted for. Physicists call it dark radiation, and it could come from exotic particles that were abundant shortly after the Big Bang, but have since decayed or diluted away. If dark radiation existed, it would change the physics of the early universe in subtle ways that would shift the Planck prediction for the Hubble constant upward, potentially closing the gap with the local measurements. Both of these ideas, evolving dark energy and dark radiation, require new physics, particles or forces that aren't part of the Standard Model, that makes them harder to test and harder to confirm. The void model has an advantage over those alternatives because it doesn't require new physics. It's a geometrical explanation, not a fundamental one. The laws of physics are the same inside the void as they are everywhere else. General relativity still works. Dark matter still clumps. Dark energy still pushes. The difference is the environment. You're in a place where the balance between gravity and dark energy is tilted toward dark energy, and that tilt changes what you measure. No new particles, no modifications to the equations, just geography. That said, the void model doesn't explain the entire Hubble tension cleanly. Most simulations suggest it can account for about half the discrepancy, maybe a bit more if you fine-tune the void's properties. That leaves several % of the tension unexplained. Some researchers think the remaining gap could be closed by accounting for other local structures. The Milky Way isn't just in a void. It's also near a supercluster called the Laniakea supercluster, a giant concentration of galaxies about 500 million light-years across that's pulling on our local group of galaxies. That infall motion could add an additional bias to local measurements. Combine the void's outward push with the supercluster's inward pull, and maybe you get the full 9%. Others think the remaining tension is a sign that multiple effects are at play. Some combination of the void, evolving dark energy, and systematic uncertainties in the measurements. The truth, as is often the case in science, is probably messier than any single clean explanation. What's undeniable is that the void model has shifted the conversation. Before Banach's paper and the work that followed, the Hubble tension was framed as a crisis in fundamental physics, a sign that either our model of the early universe was wrong or our understanding of cosmic expansion was incomplete. Since the void model gained traction, the tension is increasingly being framed as a problem of perspective. We're measuring the right things, we're just measuring them from the wrong place. That reframing doesn't solve the problem, but it changes the questions. Instead of asking what's wrong with the standard model, cosmologists are now asking, how do we correct for being in a void? How do we measure the true cosmic expansion rate when we're sitting in a region where the local rate is higher than average? How do we disentangle the signal of the void from the signal of the universe at large? Those are hard questions. Answering them requires mapping the void's boundaries with high precision, measuring the density gradient as you move from the center toward the edge, and tracking how galaxy velocities change across that gradient. Several large-scale surveys are working on exactly that. The Dark Energy Spectroscopic Instrument, DESI, is measuring redshifts for millions of galaxies across a huge volume of space. The Vera Rubin Observatory, once it comes online, will map the positions and motions of billions of galaxies in the southern hemisphere. Both of these surveys will provide the data needed to test the void model rigorously. If the model is correct, we should see a clear transition at the void's edge where the expansion rate drops back toward the cosmic average. If we don't see that transition, or if the transition doesn't match the model's predictions, then the void model is in trouble and we're back to square one. For now, the void model remains one of the most compelling explanations on the table. It doesn't require rewriting the laws of physics. It explains multiple anomalies with a single feature, and it makes testable predictions that upcoming surveys can confirm or rule out. That combination of simplicity, explanatory power, and testability is rare in cosmology. Most proposed solutions to big problems are either too complicated to test or too simple to explain the data. The void model threads that needle. It's not the final answer. It's not even a complete answer, but it's pointing in a direction that makes sense, and in a field where the Hubble tension has been called a crisis for more than a decade, any direction that makes sense is worth pursuing. And here's the thing that makes the void model genuinely unsettling. If it's correct, then every measurement of the local universe we've ever made is biased. Not just the Hubble constant, everything. The rate at which galaxies form stars, the distribution of dark matter, the frequency of galaxy mergers, the density of intergalactic gas. All of it reflects the fact that we are sitting in an underdense region, and all of it is different from what you'd measure if you were sitting in an average part of the cosmos. For a century, astronomers have been mapping the universe from Earth, assuming that what we see nearby is representative of what's happening everywhere. The KBC Void says that assumption is wrong. We're not sitting in an average neighborhood. We're sitting in a desert, and the view from a desert is not the same as the view from a forest. We've been drawing maps of the forest while standing in the desert and wondering why the trees don't line up. We've been talking about the KBC Void as if it's a problem, a statistical anomaly, a glitch in the data that needs explaining. And it is all those things, but zoom out far enough, and the void stops looking like an exception and starts looking like the rule. Because here's the uncomfortable truth that's been sitting in plain sight for decades, ignored by most of cosmology until very recently. The universe is mostly empty. Not empty in the poetic sense, the way people say space is a vacuum. Empty in the literal, measurable, undeniable sense that when you add up all the volume occupied by galaxies, stars, gas and dark matter, and compare it to the total volume of space, the stuff accounts for maybe 10%. The other 90% is voids. Enormous bubbles of near-nothingness where galaxies are rare, matter is sparse, and the cosmic web, that beautiful tapestry of filaments and clusters we've been mapping for 40 years, turns out to be just the scaffolding around an ocean of emptiness. For most of the 20th century, astronomers thought about the universe in terms of what was there. Galaxies, clusters, superclusters, giant walls of galaxies stretching across hundreds of millions of light-years. Those were the structures that mattered, the things worth cataloguing and studying. Voids were treated as leftovers, the gaps between the interesting parts, like the spaces between words on a page. Nobody spends much time analyzing blank paper. You focus on the text. But by the 1980s, as redshift surveys started mapping galaxies in 3 dimensions, a pattern emerged that was harder to ignore. The galaxies weren't scattered randomly, they lined up along filaments, thin threads of matter connecting dense nodes where clusters formed. And between the filaments there was almost nothing, not a smooth distribution with occasional dips, a sponge, a foam, a web with holes so large that you could fit dozens of Milky Way-sized galaxies across them and still have room left over. The first major void was discovered in 1981 by Robert Kirshner and his team at the Harvard-Smithsonian Center for Astrophysics. They were mapping galaxies in the constellation Bootes, a relatively unremarkable patch of sky in the northern hemisphere, when they noticed something strange. A region roughly 330 million light-years across where galaxies were missing, not entirely absent. There were about 60 galaxies scattered through the void, which sounds like a lot until you realize that an equivalent volume of average space should contain 10,000. The Bootes void, as it came to be called, was so empty that Kirshner reportedly joked it looked like someone had scooped out a chunk of the universe and forgotten to put it back. At first, the discovery was treated as an oddity. A single large void didn't challenge the standard model. The universe was allowed to have gaps. But as surveys expanded and more of the sky was mapped, more voids turned up. Hundreds of them, thousands of them. Voids weren't rare. They were everywhere. By the late 1990s, the picture was clear. The cosmic web wasn't a web with a few holes in it. It was a web made almost entirely of holes, with thin strands of matter stretched between them. The filaments, the walls, the clusters, all the structures astronomers had been cataloguing for decades, were the minority. The voids were the majority, and they occupied roughly 90% of the total volume of space. Let that sink in for a second. 90%. If you picked a random point in the universe and asked what's here, 9 times out of 10, the answer would be nothing much. A few stray galaxies drifting through a region where the density of matter is a fraction of the cosmic average. You'd have to be extraordinarily lucky or deliberately aiming for a dense region to land somewhere interesting. The stuff, the galaxies and stars and planets and people, all of it is concentrated into 10% of the available volume. The rest is desert. That realization forced cosmologists to rethink what the cosmic web actually is. For decades, the mental model was that galaxies formed everywhere, and then gravity pulled them into clusters and filaments, leaving voids behind as the regions where matter had drained away. That's partially true, but it's backwards. The voids came first. In the early universe, tiny fluctuations in density, quantum ripples from the inflationary era, created regions that were slightly more dense than average and regions that were slightly less dense. Gravity amplified those differences. Dense regions pulled in more matter and got denser. Underdense regions lost matter and got emptier. Over billions of years, the dense regions collapsed into filaments and clusters. The underdense regions expanded into voids. The cosmic web isn't a structure built on a foundation of uniformity. It's a structure carved out of emptiness. Think of it like soap bubbles. When you blow a cluster of bubbles, the soap film collects along the edges where bubbles touch, forming a network of thin walls and junctions. The interior of each bubble is empty air. The cosmic web is the same. The filaments are where matter has collected. The voids are the interiors. And just like soap bubbles, the voids are much larger than the walls around them. You can see this in simulations. Feed a computer the initial conditions of the early universe. Let dark matter clump under gravity and watch what happens. Within a few 100 million years, the smooth distribution breaks up into a web of filaments with enormous voids in between. The bigger the void, the longer it takes to empty out. But once a region starts losing matter to its surroundings, the process accelerates. Matter drains toward the filaments. The void grows. By the time the universe is a few billion years old, the structure is locked in. Filaments and voids, walls and emptiness. 10% matter, 90% not. The KBC Void fits perfectly into this picture. It's not an anomaly. It's an extreme example of something the universe does all the time. What makes it unusual is the size. Most voids are a few 100 million light-years across. The KBC Void is 2 billion light-years across, 7 times larger than average. That's big enough to raise questions about whether the standard model allows voids that large to form, but it's not big enough to break the framework entirely. Voids exist. The universe makes them. The KBC Void is just the biggest one we've found so far. And the fact that we're sitting in it says something uncomfortable about how representative our view of the cosmos really is. Because here's the thing. If you're sitting in a void, your local environment doesn't look like the cosmic average. Galaxies are farther apart. Galaxy clusters are smaller and less massive. The rate at which stars form is lower because there's less gas to collapse under gravity. Dark matter halos, the invisible scaffolding that galaxies form inside, are less dense and more spread out. Everything about the physics of structure formation is shifted toward the slow, quiet, underpopulated end of the spectrum. And if you're an astronomer sitting in that environment, every measurement you make reflects that shift. You're not seeing the universe as it is on average. You're seeing the universe as it is in a void. And for a long time, nobody realized that mattered. It matters because cosmology depends on the assumption that we occupy a typical location. The Copernican principle, the idea that we're not special, that the view from Earth is roughly the same as the view you'd get from any other random galaxy. That principle is load-bearing. If it's wrong, then every local measurement we make, every observation of the nearby universe, is biased. The Hubble constant comes out high because we're in a void. The matter density comes out low because we're in a void. The rate of galaxy formation looks slower because we're in a void. None of those measurements are wrong, they're just local, and local doesn't equal universal. The realization that voids dominate the universe's volume has also forced a rethinking of how galaxies form and evolve. For decades, the standard story went like this. Dark matter clumps into halos. Gas falls into those halos. The gas cools and collapses under its own gravity. Stars ignite. A galaxy is born. That process is supposed to be efficient in dense regions where there's plenty of gas and strong gravity to pull it together. In underdense regions, the process should be slower and less efficient because there's less gas and weaker gravity. Galaxies in voids should be smaller, dimmer, and younger than galaxies in filaments and clusters. That prediction mostly holds up. Void galaxies do tend to be less massive and less luminous than their counterparts in dense regions, but the difference isn't as large as the models predicted. Some void galaxies are just as big and just as bright as galaxies in clusters. That's a problem because it suggests the physics of galaxy formation in voids is more complicated than a simple story about low density and weak gravity. One possibility is that void galaxies form differently. In a dense region, a young galaxy is constantly being jostled by the gravity of its neighbors. Gas gets stripped away by close encounters. Mergers are common, with small galaxies crashing into larger ones and getting absorbed. The environment is violent and chaotic. In a void, galaxies are more isolated. They don't get stripped. They don't merge as often. They grow slowly and steadily, fed by thin streams of gas trickling in from the surrounding space. That isolation might allow void galaxies to hang on to their gas longer and form stars over a more extended period, which could explain why some of them are surprisingly well developed despite sitting in a region where the density is low. Another possibility is that void galaxies formed earlier than we thought. If the voids were already emptying out in the first billion years after the Big Bang, then the galaxies that did manage to form in those regions had a head start. They grabbed whatever gas was available before it drained away into the filaments, and they've been coasting ever since, forming stars slowly but steadily over billions of years. That would make void galaxies older on average than galaxies in dense regions, which is the opposite of what the standard model predicts. Some observations hint at this. Void galaxies tend to have older stellar populations and less active star formation than galaxies in clusters. They look more mature, more settled, as if they've been quietly minding their own business for a very long time. The Milky Way itself might be an example of this. Our galaxy is sitting in the middle of the KBC Void, and it's not a small or underdeveloped galaxy. It's a massive spiral with hundreds of billions of stars, a well-defined disk, and a central bulge. By most measures, the Milky Way is above average. If the void model is correct, then our galaxy formed in an underdense environment and still managed to become one of the larger galaxies in the local universe. That suggests either the Milky Way got lucky, grabbing more than its fair share of gas before the void emptied out, or the physics of galaxy formation in voids allows for more diversity than the models account for. Either way, the Milky Way is not what you'd expect to find in the middle of a giant hole. The discovery of the KBC Void has also prompted astronomers to go back and look at other known voids with fresh eyes. The Bootes Void, that 330 million light-year bubble discovered in 1981, is still one of the most famous. It's smaller than the KBC Void but more dramatically empty, with only about 60 galaxies in a region that should contain 10,000. For years, astronomers treated the Bootes Void as an outlier, a place where for some reason galaxy formation failed more completely than usual. Now it looks less like an outlier and more like a preview. If the KBC Void can exist, if 2 billion light-year underdensities are allowed by the physics, then the Bootes Void isn't strange. It's just a smaller, emptier version of the same thing. Then there's the Eridanus supervoid, a massive underdense region sitting about 3 billion light-years away in the constellation Eridanus. The Eridanus supervoid is interesting because it's been linked to the cold spot, that anomalous region in the cosmic microwave background where the temperature is slightly lower than it should be. The leading explanation for the cold spot is that microwave photons traveling through a supervoid lose energy climbing out of its gravitational well, arriving at our telescopes slightly cooler than photons that didn't pass through a void. If that explanation is correct, then the Eridanus supervoid is even larger than it appears, possibly exceeding 1 billion light-years in size. That would make it comparable to the KBC Void, And it would mean the universe has at least two enormous voids within observable distance of Earth. That's either a coincidence or a sign that voids this large are more common than the statistical models predict. The statistical question is where things get uncomfortable. According to simulations based on the standard model of cosmology, voids larger than about 500 million light-years should be extremely rare. A 2 billion light-year void like the KBC Void should occur less than once per observable universe. The fact that we're sitting in one, and that there might be other voids of similar size within a few billion light-years, suggests either we're extraordinarily unlucky or the models are missing something. Indranil Banik, the researcher who calculated that the KBC Void is a 10 sigma statistical anomaly, argued that the void's existence is evidence the standard model needs revising. He's not alone. A growing number of cosmologists are starting to think that the assumptions underpinning structure formation, specifically the way dark matter clumps and the efficiency with which gas turns into galaxies, might need adjusting. Maybe voids grow larger than the simulations predict. Maybe the early universe had more pronounced density fluctuations than we've accounted for. Maybe the cosmological principle, the idea that the universe is homogeneous on large scales, is true on average but breaks down badly in specific regions. That last possibility is the most philosophically destabilizing because it undermines the foundation cosmology is built on. If the universe is lumpy at scales larger than a few 100 million light-years, then you can't treat it as a smooth fluid with small perturbations on top. You have to account for the lumpiness, and that makes the math much harder. The equations of general relativity that describe cosmic expansion assume a uniform distribution of matter and energy. If the distribution isn't uniform, the equations give you different answers depending on where you're sitting. The expansion rate in a void is different from the expansion rate in a supercluster. The age of the universe calculated from local measurements is different from the age calculated from the cosmic microwave background. Cosmology stops being a single universal story and starts being a collection of local stories stitched together. That's not wrong. The universe doesn't care whether the math is convenient, but it does mean that every result, every measurement, every conclusion comes with an asterisk. Valid here, not necessarily valid there. There's also a psychological dimension to the void that's hard to articulate but impossible to ignore. For most of human history, the universe felt full. The night sky was crowded with stars. The Milky Way stretched overhead like a river of light. Everywhere you looked, there was something. Then telescopes revealed that the stars were suns, that the suns were gathered into galaxies, and that the galaxies were clustered into vast structures spanning unimaginable distances. The universe got bigger, but it still felt full, packed with matter, dense with possibility. The discovery that 90% of space is empty changes that feeling. It suggests the universe is not a crowded place where interesting things are happening everywhere. It's a sparse place where interesting things are concentrated into narrow threads and isolated nodes, and the rest is silence. The KBC Void makes that emptiness personal. It's not just that voids exist out there somewhere in the distant cosmos. We're in one. The Milky Way, the Sun, the Earth, every person who has ever lived, all of it is sitting in a region where the density of matter is 20 to 50% below average. We're not in the thick of things, we're in the outskirts, the backwater, the quiet corner where not much happens and not much ever will. That doesn't change the fact that stars formed here, that planets coalesced, that life emerged and evolved and eventually started asking questions about where it was. But it does change the context. We're not sitting in the bustling downtown of the cosmic web, we're sitting in the suburbs. And the suburbs, as anyone who's lived in them knows, are quieter, emptier, and less connected to the action than the mental maps we draw would suggest. Some researchers have even speculated that the void might be connected to the Fermi paradox, the question of why we haven't detected any signs of intelligent life elsewhere in the universe. If the KBC Void delayed galaxy formation in our region, if stars and planets took longer to form here than they did in denser parts of the cosmos, then life in the void might be younger on average than life elsewhere. Civilizations in the filaments and clusters might have had a billion-year head start. By the time we arrived, they could already be ancient, post-biological, uninterested in broadcasting their presence to every emerging species with a radio telescope. Or they could have burned out, collapsed, gone extinct, leaving nothing but ruins too faint to detect across billions of light-years. The void doesn't explain the Fermi paradox, but it adds a layer. If you're looking for life, you're more likely to find it where galaxies are dense, where stars form quickly, where planets are abundant. Voids are not where you'd expect the action to be, and yet here we are, asking questions, building telescopes, mapping the structure of the universe, and discovering that the structure is mostly empty. There's something almost poetic about that. The fact that intelligence emerged in a void, in a place where the odds were stacked against complexity, where the density was low and the gravitational environment was weak, and galaxies formed slowly if at all. We're the exception that proves the rule. The unlikely observers sitting in the quiet part of the cosmos, looking outward at the noise and trying to make sense of it. The cosmic web, as we understand it now, is not what we thought it was 40 years ago. It's not a tapestry of galaxies with occasional gaps. It's a skeleton of filaments surrounding vast, empty chambers. The filaments are where the matter is. The chambers are where the volume is. And the chambers, the voids, are not passive leftovers. They're active participants in the story of structure formation. They shape how galaxies move, how clusters grow, how the universe expands. They occupy most of the space. They define the geography, and ignoring them, treating them as unimportant because they're empty, is like trying to understand a building by only looking at the walls and ignoring the rooms. The realization that voids are the dominant feature of the universe has practical implications too. If you're planning a galaxy survey, you need to account for the fact that most of your observing volume is going to be empty. If you're trying to map the distribution of dark matter, you need to measure not just where it is, but where it isn't, because the absence of dark matter in voids tells you as much about how structure forms as the presence of dark matter in filaments. If you're trying to understand the Hubble constant, or the matter density, or the rate of cosmic expansion, you need to know whether your measurements are coming from a void, a filament, or a cluster, because the answer changes depending on where you are. And that brings us full circle. The KBC Void is not an isolated curiosity. It's a window into the larger truth that the universe is mostly empty, and that emptiness matters. It changes the physics, it biases the measurements, it reshapes our understanding of where we are and what we're looking at. For a century, cosmology has been built on the assumption that the universe is uniform on large scales and that our local measurements reflect that uniformity. The void says that assumption is wrong. We're not sitting in an average place, we're sitting in a hole, and the view from a hole is not the same as the view from anywhere else. The universe is not the dense, crowded, galaxy-filled expanse we once imagined. It's a sparse web of matter stretched across an ocean of emptiness. And the fact that we exist in that emptiness, that we evolved here and built civilizations here and pointed telescopes at the sky here, is either the universe's idea of a joke or a reminder that the most interesting things don't always happen where you'd expect them to. Sometimes they happen in the quiet places, the deserts, the voids, the 90% of space where nothing much is going on, and yet somehow, against the odds, something did. Here's the thing about scientific revolutions. They don't announce themselves. They don't arrive with trumpets and a carefully worded press release explaining that everything you thought you knew is about to be overturned. They start quietly, with a measurement that doesn't quite fit, a result that's slightly off, a number that refuses to behave, and for a while, everyone assumes it's a mistake. The instruments were miscalibrated, the data was contaminated, someone forgot to carry the one. Then more measurements come in, different teams, different methods, same problem, the number is still wrong. And at some point, usually later than it should be, someone looks up from their spreadsheet and says the sentence that changes everything. What if the model is broken? The KBC Void has brought cosmology to that point. Not loudly, not dramatically, but persistently. For more than a decade, the void has been sitting in the data like a loose thread in a sweater. Pull on it gently and nothing happens. Pull harder and the whole thing starts to unravel. The Hubble tension, the discrepancy between how fast the universe appears to be expanding locally versus how fast it should be expanding based on the early universe, is that thread, and the void is the hand pulling on it. If the void explains the Hubble tension, and there's growing evidence it might, then the implications ripple outward far beyond a single number. Because resolving the tension by invoking the void means accepting that we've been measuring the universe from inside an anomaly. And once you accept that, everything downstream has to be recalculated. The Hubble constant, the age of the universe, the density of dark energy, the timeline of structure formation, all of it shifts, not because the physics changed, because the geography did. But here's where it gets uncomfortable. If the void is real, if it's as large and as underdense as the measurements suggest, and if it formed in the time available since the Big Bang, then the standard model of cosmology has a problem. Not a small problem, a foundational problem. The standard model, formerly called lambda cold dark matter, lambda CDM for short, is built on a set of assumptions that have worked beautifully for decades. The universe is homogeneous on large scales. Structure forms hierarchically, with small clumps merging into larger ones over billions of years. Dark matter provides the gravitational scaffolding. Dark energy drives accelerated expansion. Plug in the initial conditions from the cosmic microwave background, let the equations run, and you get a universe that looks a lot like the one we observe. Galaxies, clusters, filaments, voids, all of it emerges naturally from the math, except the voids that emerge from the simulations are smaller than the KBC void, much smaller. The largest voids predicted by lambda CDM top out at around 500 million light-years. Anything significantly bigger is exponentially rare. A 2 billion light-year void, by some calculations, should occur less than once per observable universe. That's the 10 sigma problem Indranil Banik calculated. 10 sigma means the probability of the void existing by chance under the standard model is so low that you'd have to run the universe trillions of times before you'd expect to see one. And yet here it is, which means either we won the worst lottery in the history of probability, or the model that predicts void sizes is missing something. The first instinct, the conservative instinct, is to tweak the model. Maybe the initial conditions in our patch of space were slightly different from the cosmic average. Maybe the density fluctuations in the early universe were more pronounced here, allowing a larger underdensity to grow. Maybe the efficiency with which matter drains out of voids and into filaments is higher than the simulations assume. All of those are plausible. All of them involve adjusting parameters within the existing framework rather than overhauling the framework itself. That's how science usually works. You don't throw out a model the first time it produces a surprising result. You refine it. You add complexity. You see if the problem goes away. But what if it doesn't? What if, after refining the model and adjusting the parameters and rerunning the simulations, the KBC void is still too large, too underdense, too statistically improbable to explain without breaking something? Then you're left with two options. Accept that we live in an extraordinarily unlikely place, a cosmic fluke so rare that finding ourselves here borders on suspicious. Or accept that the model is incomplete, and something about the way we understand structure formation, cosmic expansion, or even gravity itself needs revising. That second option is where things get interesting and unsettling. The cosmological principle is the bedrock of modern cosmology. It states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. Zoom out past a few 100 million light-years, and the lumps and voids and filaments should average out into a smooth, uniform distribution of matter and energy. That principle is not just a philosophical nicety. It's mathematically necessary. The equations of general relativity that describe how the universe expands, the Friedmann equations, assume a smooth universe. Feed them a lumpy universe and the math breaks. Different regions expand at different rates. The expansion history depends on where you're sitting. The Hubble constant stops being a constant. It becomes a local variable. For decades, observations supported the cosmological principle. The cosmic microwave background is smooth to 1 part in 100,000. Galaxy surveys showed structure on small and medium scales, but when you averaged over volumes larger than 300 million light-years, the density evened out. Everything fit. Then the KBC void showed up, a 2 billion light-year underdensity centered on the Milky Way, and the principle started looking shaky. A structure that large doesn't average away. It dominates the local volume. And if similar structures exist elsewhere, which they probably do, then the universe on large scales is lumpier than the cosmological principle allows. The smoothing scale, the distance at which the universe stops being clumpy and starts being uniform, might be larger than we thought, much larger, or it might not exist at all. The universe might be lumpy all the way up. If that's true, then the Friedmann equations, the foundation of cosmology, are at best an approximation that works on average but fails locally. At worst, they're wrong, not in a way that overturns general relativity entirely. General relativity is still the best description we have of how gravity works. But it's possible we've been using the wrong version of the equations. The Friedmann equations assume a perfectly smooth universe. Real universes are not smooth. They're full of galaxies and clusters and voids. Accounting for that lumpiness requires more complicated math, a framework called inhomogeneous cosmology. Instead of treating the universe as a single expanding fluid, you treat it as a patchwork of regions with different densities, each expanding at slightly different rates. The overall expansion is the average, but the local expansion depends on where you are. Inhomogeneous cosmology has been around since the 1960s, but it's hard. The equations are messy, the simulations are computationally expensive, and for a long time it seemed unnecessary because the Friedmann equations worked so well. Why complicate things if the simple version gives you the right answer? The KBC void is the reason. If the void is causing the local expansion rate to differ from the cosmic average by 9%, which is what the Hubble tension suggests, then the simple version is not giving you the right answer. You need the complicated version. And once you start using the complicated version, other things change too. For one, dark energy stops looking like a constant. In the standard model, dark energy is described by the cosmological constant, lambda, the same lambda in lambda CDM. It's a property of empty space itself, a kind of intrinsic pressure that pushes outward, making the universe expand faster over time. The strength of the cosmological constant is the same everywhere and doesn't change with time. It's a number you plug into the equations once and forget about. But in an inhomogeneous universe, dark energy's effects depend on the local density. In a dense region, gravity fights back, and dark energy's influence is muted. In a void, gravity is weak, and dark energy dominates. The cosmological constant is still constant, but its observable effects are not. What you measure as the local expansion rate reflects the balance between gravity and dark energy in your region, not the cosmic average. That distinction matters because it changes how we interpret measurements of dark energy. For 25 years, astronomers have been using distant supernovae to trace the universe's expansion history, looking for signs that dark energy is evolving over time. The results have consistently shown that dark energy behaves like a cosmological constant. Its strength doesn't change, but those measurements assume a homogeneous universe. If the universe is lumpy, and if we're sitting in one of the lumps, or rather one of the holes, then the measurements are biased. We're not measuring dark energy's true strength. We're measuring how dark energy behaves in a void. And that measurement might be higher than the cosmic average. The void model says the local expansion rate is elevated not because dark energy is stronger here, but because there's less matter to slow it down. The effect looks the same. The cause is different. Some researchers have taken this idea further and proposed that dark energy itself might not be a cosmological constant at all. Maybe it's a field, something dynamic that can vary in strength depending on the environment. Physicists call this idea quintessence, named after the fifth element in ancient philosophy. Quintessence behaves like dark energy on large scales, pushing the universe apart, but unlike the cosmological constant, its strength can change over time or from place to place. In a dense region, quintessence might be weaker. In a void, stronger. That variability could explain why the local Hubble constant is high without requiring the void to be as underdense as the measurements suggest. The void is still there, but part of the effect comes from dark energy being more active in underdense regions. Quintessence is speculative. No one has detected it. No one has a compelling model for what kind of field it would be or why it would vary the way it does. But the idea has gained traction because it offers a way to explain multiple anomalies at once. The Hubble tension. The fact that some distant supernovae seem to be dimmer than they should be. The cold spot in the cosmic microwave background. All of those could be symptoms of a universe where dark energy is not constant but dynamic, shaped by the local distribution of matter. If that's true, then the cosmological constant, the lambda in lambda CDM, is an approximation, a useful one on average, but not the full story. There's another possibility that's even more radical. Maybe gravity itself works differently on cosmic scales. General relativity has passed every test we've thrown at it for more than a century. It describes how planets orbit stars, how light bends around black holes, how gravitational waves ripple through space-time. But all of those tests happen in relatively strong gravitational fields, solar systems, galaxies, binary neutron stars. On the largest scales, where gravity is weak and distances are measured in billions of light-years, we've never tested general relativity directly. We've only tested it indirectly by assuming it works and checking whether the predictions match observations, and for a long time they did. But the KBC Void, combined with the Hubble tension, raises the possibility that general relativity breaks down at cosmic scales. Not dramatically, not in a way that makes planets fall out of orbit, but subtly, in a way that changes how structure forms and how the universe expands. Modified gravity theories have been around for decades, usually proposed as alternatives to dark matter. The most famous is modified Newtonian dynamics, MUN-D, which tweaks the laws of gravity to explain why galaxies rotate faster than visible matter alone would allow. MUN-D has problems. It doesn't explain galaxy clusters or the cosmic microwave background as well as dark matter does, but some researchers think MUN-D or something like it might explain why the universe has voids as large as the KBC Void. The argument goes like this. In a standard gravity universe, structure forms hierarchically. Small clumps merge into larger ones. Voids grow by draining matter into surrounding filaments, but the process is slow and self-limiting because gravity pulls back. In a modified gravity universe, where the strength of gravity drops off faster at large distances, the draining process is more efficient. Matter escapes voids more easily. Voids grow larger. The KBC Void, under this scenario, is not an improbable fluke. It's a natural consequence of gravity behaving differently than general relativity predicts at distances larger than a few 100 million light-years. Modified gravity theories are controversial. Most cosmologists think dark matter explains the data more cleanly and that invoking new physics to explain voids is unnecessary, but the void's existence has given modified gravity a second look. If lambda CDM can't produce voids as large as the KBC Void without invoking 10 sigma probabilities, and modified gravity can, then maybe the theory deserves more attention. The test will come from future observations. If modified gravity is correct, it should make different predictions about how galaxies move in voids, how structure forms over time, and how the expansion rate varies with distance. If those predictions match the data better than lambda CDM, the theory gains credibility. If they don't, it fades back into obscurity. There's also the question of what the void means for the early universe. Lambda CDM assumes that the tiny density fluctuations visible in the cosmic microwave background grew into the cosmic web we see today. Those fluctuations are almost perfectly Gaussian, meaning they're random and follow a smooth statistical distribution. But the KBC Void, if it's as large as it appears, might require the initial fluctuations to be non-Gaussian, more extreme, with larger peaks and deeper troughs than the standard model predicts. Non-Gaussian fluctuations could arise from modifications to inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. Standard inflation produces Gaussian fluctuations. Non-standard inflation, involving multiple fields or unusual dynamics, can produce non-Gaussian ones. If the void's existence forces us to revisit inflation, that's a big deal. Inflation is one of the most successful ideas in cosmology. It explains why the universe is so flat, so smooth, and so uniform on large scales. It explains where the density fluctuations that seeded galaxies came from. And it makes predictions that have been tested and confirmed by observations of the cosmic microwave background. But inflation is also frustratingly flexible. There are hundreds of models, each tweaking the details in different ways, and most of them produce universes that look roughly like ours. The KBC Void could be a way to narrow the field. If only certain inflation models produce fluctuations large enough to grow into 2 billion light-year voids, then those are the models worth focusing on. The void becomes a fossil of the universe's first moments, a clue to the physics that operated when everything was smaller than an atom. Some researchers have gone even further and suggested that the void points toward new fundamental particles, not dark matter, which is already hypothetical enough, but something else. A field or particle that interacts weakly with normal matter and dark matter but strongly with itself, creating regions where it clumps unusually or repels unusually. The effect would be subtle, barely detectable in most environments, but amplified in the largest voids where the density is low and the gravitational landscape is simple. That kind of particle would show up as anomalies in structure formation, unexpectedly large voids, unexpectedly smooth regions in the cosmic microwave background, and deviations in the Hubble constant, which is exactly what we're seeing. Whether such a particle exists is anyone's guess. No one has detected it. No one has a compelling theory for what it would be or why it would behave the way it does. But the fact that the void's existence seems to require something beyond lambda CDM has opened the door to speculation, and speculation is where new physics often starts. The process of paradigm shifts in science is not as clean as textbooks make it sound. The story we tell ourselves goes like this. A theory works for a while. New data comes in that contradicts the theory. Scientists propose alternatives. The alternatives are tested. One of them works better than the old theory. The field adopts the new theory. Revolution complete. That's the simplified version. The real version is messier. Theories don't fail all at once. They fail gradually, in pieces, with lots of argument and confusion along the way. Some scientists cling to the old theory, tweaking it to accommodate the new data. Others jump to the new theory prematurely before it's been tested enough to deserve confidence. Most sit in the middle, waiting for more evidence, hedging their bets and quietly wondering whether they're witnessing the collapse of a framework or just a rough patch that will smooth out with better measurements. Cosmology is in that messy middle right now. Lambda CDM still works for most things. It explains the cosmic microwave background. It explains the large-scale distribution of galaxies. It explains the abundance of light elements forged in the Big Bang. It's not wrong in the way the Earth-centered universe was wrong, where every new observation made the model more ridiculous until it collapsed under its own absurdity. Lambda CDM is still standing, but it's creaking. The Hubble tension won't go away. The KBC Void is larger than it should be. Some early galaxies observed by the James Webb Space Telescope are more massive than the model predicts they could be at their distances. Each of those problems individually could be a fluke or a misunderstanding. Taken together, they look like cracks. And the question cosmologists are quietly asking each other, in conferences and emails and late-night conversations over drinks, is whether the cracks are repairable or whether the whole structure needs rebuilding. The KBC Void sits at the center of that question because it's big enough and well measured enough that it can't be easily dismissed. It's there, the density is low, the size is 2 billion light-years. The Milky Way is near the middle. Those are facts, not speculation. What those facts mean is the argument. Do they mean lambda CDM is missing a parameter? Do they mean the cosmological principle breaks down at larger scales than we thought? Do they mean gravity behaves differently in low-density regions? Do they mean dark energy is not a constant? Do they mean inflation was more complicated than the standard models allow? Or do they just mean we're sitting in an unlikely place and the universe, indifferent to our need for statistical comfort, doesn't care? The answer will come from observations, lots of them. Over the next decade, multiple large-scale surveys will map the structure of the universe in unprecedented detail. The Dark Energy Spectroscopic Instrument is measuring redshifts for tens of millions of galaxies, tracing how the cosmic web has evolved over billions of years. The Vera Rubin Observatory will photograph the entire southern sky every few nights, building a time-lapse map of the cosmos that will reveal how galaxies move and how structure grows. The Euclid satellite is mapping the shapes and positions of billions of galaxies to measure the distribution of dark matter with exquisite precision, and the James Webb Space Telescope is peering back to the earliest galaxies, looking for signs of how structure formed when the universe was young. All of those surveys will test lambda CDM in ways we've never been able to before. They'll measure the size distribution of voids, They'll track how galaxies move in underdense regions. They'll search for deviations in the Hubble constant as you move from voids to filaments to clusters. If lambda CDM is right, the data will confirm it. If it's wrong, the data will show where it breaks. The KBC Void is the test case. If future surveys confirm that the void is as large as current measurements suggest, and if simulations can't reproduce it without exotic physics, then the field will have to adapt. That adaptation might be minor, a tweak to the initial conditions, a revised estimate of how efficiently structure forms, or it might be major. A modified theory of gravity, a dynamic dark energy field, a new particle, a fundamental rethinking of how the universe works on its largest scales. Scientists don't know yet which it will be. They're waiting for the data, and the data is coming. What makes this moment in cosmology so tense is that everyone knows the stakes. If the void forces a paradigm shift, it won't be the first time cosmology has had to reinvent itself. In the 1920s, Edwin Hubble's discovery that the universe was expanding overturned the static universe model that had stood for centuries. In the 1960s, the discovery of the cosmic microwave background killed the steady-state theory and confirmed the Big Bang. In the 1990s, the discovery that the universe's expansion was accelerating forced the introduction of dark energy, a concept so strange that even the scientists who discovered it struggled to accept it. Each of those shifts was resisted at first, then grudgingly accepted, then integrated into a new framework that worked better than the old one. The KBC Void might be the next shift, or it might be a footnote, an anomaly that gets explained away as better data rolls in. Either way, the process is the same. Measure, test, argue, refine, and eventually slowly figure out what the universe is actually doing. The void has already changed the conversation. 5 years ago, the Hubble tension was framed as a crisis in fundamental physics, a sign that either dark energy or the early universe or the expansion itself was behaving in ways we didn't understand. Now, increasingly, it's framed as a problem of geography. We're measuring the right things. We're just measuring them from the wrong place. That reframing doesn't solve the problem, but it shifts the question. Instead of asking what's wrong with the model, cosmologists are asking, how do we account for being in a void? How do we correct for the bias? How do we measure the true cosmic expansion rate when our local rate is elevated? Those are still hard questions, but they're different questions. And the fact that the field is asking them means the void has already reshaped the landscape. There's a quote from the physicist Max Planck that gets repeated a lot in moments like this. Science advances one funeral at a time, the idea being that old ideas don't die because scientists are convinced by new evidence. They die because the scientists who believed the old ideas retire or pass away, and a new generation trained in the new framework takes over. That's cynical but not entirely wrong. Paradigm shifts take time. Careers are built on models. Reputations are staked on predictions. Admitting the model is broken feels like admitting you wasted decades working on the wrong thing. So people resist. They argue, they defend, and eventually, as the evidence piles up and the old guard fades, the field moves on. The KBC Void is not there yet. Lambda CDM is still the dominant framework. Most cosmologists think the model will survive with modifications rather than being replaced entirely, but the void has planted doubt, and doubt in science is where progress begins. The most exciting discoveries don't come from confirming what you expected. They come from finding something that doesn't fit and following that thread until the whole picture changes. The void is that thread. Whether pulling on it unravels the sweater or just fixes a loose seam is the question the next decade of observations will answer. And whatever the answer is, cosmology won't look the same afterward. The void, 2 billion light-years wide and sitting right beneath our feet, has made sure of that. We've spent the last 6 chapters pulling apart the discovery of the KBC Void, unpacking what it means, what it challenges, and what it might explain. We've traced the history of how astronomers realized we were sitting in the middle of a 2 billion light-year underdensity. We've mapped the strange physics that operates inside it. We've walked through how the void might resolve the Hubble tension, the single most frustrating discrepancy in modern cosmology, and we've explored the uncomfortable possibility that the void's existence means something fundamental about the standard model, lambda CDM, is incomplete or broken. That's a lot of ground, a lot of questions raised, a lot of assumptions overturned. But here's the thing about scientific discoveries that challenge the foundations of a field. They don't end with a neat resolution. They end with more questions, better questions, harder questions, questions that couldn't have been asked before because we didn't know enough to ask them. The KBC Void has done exactly that. It has pushed cosmology to the edge of its current understanding and pointed outward toward the unmapped territory beyond. And what comes next? The observations, the missions, the theoretical work that will define the next decade of cosmology is where the story gets interesting. Because the void is not the end point, it's the beginning. A signpost marking the limits of what we thought we knew and the start of what we're about to figure out. And figuring it out is going to require new tools, new data, and a willingness to entertain ideas that would have seemed absurd 20 years ago. The good news is that those tools are already being built. Some of them are already online, collecting data, mapping the universe with a precision that would have been unimaginable a generation ago. Others are scheduled to launch within the next few years, carrying instruments designed specifically to answer the questions the void has raised. Cosmology in the 2020s is not sitting around waiting for the universe to reveal its secrets. It's actively hunting them down. And the void is target number 1. Start with Euclid. The European Space Agency's Euclid satellite launched in July 2023 and is currently sitting at a gravitationally stable point about 1 million miles from Earth, staring at the sky. Euclid's job is deceptively simple. Map the shapes, positions, and distances of 2 billion galaxies across a third of the sky. 2 billion galaxies. That's not a survey. That's a census. Euclid is equipped with a visible light camera and a near-infrared spectrometer, and over the course of 6 years it will measure the redshifts of tens of millions of galaxies, tracing how the cosmic web has evolved over the last 10 billion years. The goal is to understand dark energy, to map how the universe's expansion has accelerated over time, and to test whether the cosmological constant really is constant or whether dark energy is something more dynamic. But Euclid is also perfectly positioned to study voids, because to understand dark energy you need to understand the distribution of matter, where it clumps, where it doesn't, how galaxies move through underdense regions, how the expansion rate changes as you transition from a void to a filament to a cluster. Euclid's maps will show all of that in unprecedented detail. And one of the first things those maps will do is confirm or refine the boundaries of the KBC Void. Where does the underdensity end? How sharp is the transition to average density regions? Is the void's center really where we think it is? Or is the Milky Way sitting slightly off-center, closer to one wall than the other? Those details matter because they change how much the void affects local measurements of the Hubble constant. A sharper boundary means a more dramatic transition. A gradual gradient means the effect is spread out over a larger volume. Euclid will settle those questions with data, not models. And Euclid won't be working alone. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in late 2027, is coming online with a mission profile that overlaps significantly with Euclid's. Roman is equipped with a wide-field infrared camera that can image a patch of sky 100 times larger than the Hubble Space Telescope's field of view in a single exposure. That speed and coverage means Roman will survey enormous volumes of space in a fraction of the time it would take other telescopes. Over the course of its 5-year mission, Roman will map the positions and velocities of hundreds of millions of galaxies, looking for patterns in how they move, how they cluster, and how their distribution has changed over cosmic time. Roman's infrared sensitivity is particularly useful for studying voids because voids contain faint, low-mass galaxies that are hard to detect in visible light but glow brightly in the infrared. By cataloging those faint galaxies, Roman will fill in the gaps in our maps of underdense regions. Right now, we know the KBC Void has fewer galaxies than average, but we don't know exactly how many it has or how they're distributed. Are they scattered randomly, drifting through empty space like isolated islands? Or are they clustered into small filaments and groups, a miniature version of the cosmic web? Roman will answer that. And the answer will tell us whether the void formed from a smooth primordial underdensity that never attracted much matter, or whether it started with structure that later got stripped away as matter drained into the surrounding filaments. Then there's the Dark Energy Spectroscopic Instrument, DESI, which is already operational. DESI is not a space telescope. It's a ground-based instrument mounted on the Mile telescope in Arizona, and it's doing something no other survey has ever attempted at this scale. It's measuring the redshifts of 40 million galaxies and quasars scattered across 11 billion years of cosmic history. 40 million. The goal is to trace the three-dimensional structure of the universe with enough precision to see how the cosmic web has evolved over time, how dark energy has shaped that evolution, and whether the expansion rate has changed in ways the standard model doesn't predict. DESI's data is critical for understanding voids because it covers such a vast volume. The KBC Void is large, but it's local. It's sitting within 1 billion light-years of the Milky Way, which in cosmic terms is our backyard. To know whether the void is a statistical fluke or part of a larger pattern, you need to look farther. Are there other voids of similar size scattered across the universe? Are they common at certain epochs, more frequent in the early universe when structure was still forming, or in the late universe after billions of years of matter draining into filaments? DESI's maps will show that. And if it turns out that 2 billion light-year voids are not as rare as lambda CDM predicts, then the model has a problem, a big one, because rare structures are explainable. Common structures that shouldn't exist mean the physics is wrong. DESI has already released preliminary data, and the results are intriguing. Early maps show hints of enormous voids at high redshifts, distances corresponding to when the universe was only a few billion years old. Those voids are harder to map than nearby ones because the galaxies are fainter and the data is noisier, but the signal is there. If those early voids turn out to be as large as the KBC Void, it would suggest that the universe has been producing giant underdensities since very early in its history. That would be consistent with the idea that voids like the KBC Void are primordial, seeded by quantum fluctuations during inflation, and expanded by billions of years of structure formation. It would also mean lambda CDM's predictions about void sizes need revising, because the current models don't produce voids that large that early. Beyond the big surveys, there's the James Webb Space Telescope, which is technically designed to study the early universe but is increasingly being used to map the local cosmos in ways Hubble never could. Webb's infrared cameras can see through dust and detect faint galaxies at distances where Hubble would see nothing. That makes it ideal for studying the edges of voids, where galaxies are sparse and the light is dim. Several research teams are using Webb to image galaxies at the boundary of the KBC Void, looking for signs of how structure transitions from underdense to average. Do the galaxies near the edge look different from galaxies in the interior? Are they more massive, more active, forming stars more rapidly because they're being fed by gas draining out of the void? Or are they quieter, older, the last stragglers left behind as the void emptied out? Webb will answer those questions with images and spectra so detailed that you can see individual star-forming regions within galaxies billions of light-years away. And then there are the gravitational wave observatories, LIGO and Virgo, the instruments that detected the first gravitational waves from colliding black holes in 2015, are being upgraded to detect fainter signals from farther away. By the late 2020s, those upgrades will allow them to detect neutron star mergers and black hole collisions across most of the observable universe. Gravitational waves travel through space undisturbed by matter or radiation. They don't get absorbed by dust or scattered by gas. They arrive at Earth carrying information about the gravitational environment they passed through. And if those waves travel through a void, where the density of matter is lower than average, their propagation is subtly affected. The waves arrive slightly earlier or slightly later than they would if they'd traveled through an average density region. That time delay is tiny, measured in microseconds, but it's detectable if your instruments are precise enough. And by measuring those delays across many events, astronomers can map the distribution of matter along the line of sight. Voids show up as regions where the gravitational waves propagate slightly faster because there's less mass to slow them down. This technique, called gravitational wave cosmography, is still in its infancy, but it's one of the few ways to directly measure the density of dark matter in voids. Because dark matter doesn't emit light and can only be detected through its gravitational effects. Gravitational waves are sensitive to those effects in ways electromagnetic radiation is not. In the next decade, gravitational wave observatories will add an entirely new dimension to our maps of the KBC Void and voids like it. They'll show not just where visible galaxies are, but where the dark matter is. And if the dark matter distribution in the void differs from what Lambda CDM predicts, that's another crack in the model. All of these missions, Euclid, Roman, Desi, Webb, LIGO, Virgo, are converging on the same goal: map the universe with enough precision to test whether the standard model holds up at the largest scales, and the void is the test case. It's large enough to matter, it's close enough to map in detail, and it's already producing results that don't quite fit. If the next decade of observations confirms that the void is as large, as underdense, and as statistically improbable as current data suggests, then cosmology will have to adapt. That adaptation might be modest: a tweak to the initial conditions, a revised estimate of how structure forms, or it might be dramatic: a new understanding of dark energy, a modified theory of gravity, a fundamental rethinking of the cosmological principle. The data will decide, and the data is coming, but observations alone won't solve the puzzle. You also need theory, models, simulations, ways to take the data and turn it into understanding. That's where the next generation of theoretical work comes in, because the void is not just an observational challenge, it's a conceptual one. Lambda CDM was built on the assumption that the universe is smooth on large scales and that local measurements reflect the cosmic average. The void says that assumption is shaky, so theorists are now asking, what happens when you relax it? What does cosmology look like in a universe where large-scale inhomogeneities are the rule rather than the exception? Inhomogeneous cosmology, the framework that accounts for the lumpiness of the universe, has been around since the 1960s but was largely ignored because the math is hard and the Friedmann equations, which assume a smooth universe, worked well enough. The KBC Void has brought inhomogeneous cosmology back into the mainstream. Researchers are running simulations that model the universe not as a single expanding fluid, but as a patchwork of regions with different densities, each expanding at slightly different rates. Those simulations are computationally expensive. You have to track millions of particles representing dark matter, gas and galaxies over billions of years, accounting for gravity, gas dynamics, star formation and feedback from supernovae. But the payoff is enormous, because those simulations can predict what the universe should look like if lambda CDM is correct, and compare that to what we actually see. Early results are mixed. Some simulations produce voids as large as the KBC void, but only if you fine-tune the initial conditions in ways that feel arbitrary. Others produce smaller voids no matter what parameters you use. The discrepancy suggests that either we're still missing something about how voids form, or we're still missing something about how the early universe set the stage for structure formation. Either way, the simulations are closing in on the answer. And as observational data from Euclid and Roman comes in, the simulations will get better, more constrained, more accurate. Within a decade, we should have simulations that can reproduce the observed void distribution across the universe. And if those simulations require physics beyond lambda CDM to work, that's the signal that the model needs replacing. There's also theoretical work being done on how the void affects specific observations. The Hubble tension is the obvious example. If the void causes the local expansion rate to appear higher than the cosmic average, by how much? The answer depends on the void's density profile, its size, and where we're sitting inside it. Indranil Banik's 2020 paper calculated that the void could inflate the local Hubble constant by about 11%, which overshoots the observed 9% discrepancy slightly. Other researchers have done similar calculations and gotten slightly different answers depending on their assumptions. The next step is to refine those calculations with real data. Once Euclid and Roman map the void's boundaries, theorists can plug the actual density profile into their models and see if the predicted effect matches the observed Hubble tension. If it does, the void model gains credibility. If it doesn't, the field moves on to other explanations. The void is also being studied as a natural laboratory for testing fundamental physics. In a typical region of the universe, galaxies are surrounded by other galaxies. Their motion is influenced by the gravity of nearby clusters, by tidal forces, by the complex gravitational landscape of the cosmic web. In a void, galaxies are more isolated. Fewer neighbors, weaker gravitational pulls. That isolation makes voids ideal places to test theories about how gravity works on large scales. If general relativity is correct, galaxies in voids should move in predictable ways, their velocities determined by the distribution of matter around them. If modified gravity theories like MOND are correct, galaxies in voids should move differently, their velocities reflecting the altered gravitational law that MOND proposes. Several research groups are using void galaxies to test exactly that. They're measuring the peculiar velocities of galaxies inside the KBC void and comparing them to predictions from lambda CDM and from modified gravity. The results so far are inconclusive. Some void galaxies move faster than lambda CDM predicts, others move slower. The scatter is large and the measurements are noisy. But as the data improves, the test will get sharper. Within a few years, we should know whether the motion of void galaxies is consistent with general relativity or whether it points towards something else. That might sound like a niche question, but it's not. If modified gravity works better in voids than lambda CDM does, that's evidence the theory deserves serious attention, and evidence is what separates speculation from science. The void is also prompting cosmologists to think harder about what it means to measure the properties of the universe from a biased location. If the Milky Way is sitting in an underdensity, then every measurement we make of the local cosmos is skewed. The Hubble constant is higher, the matter density is lower, the rate of structure formation is slower. How do you correct for that? One approach is to map the void in such detail that you can model its effects and subtract them from your measurements. That's what Euclid and Roman are enabling. Another approach is to look farther, past the void's edge, and measure the universe in regions that are closer to the cosmic average. DESI is doing that. A third approach is to use the cosmic microwave background, which averages over the entire observable universe and isn't biased by local structure. That's what the Planck satellite did. The trick is figuring out how to combine all three approaches into a single coherent picture. How do you reconcile measurements that are inherently local with predictions that are inherently global? That's not just a technical problem. It's a conceptual one, and solving it will require new ways of thinking about what a measurement means when the measurer is sitting inside an anomaly. There's also the possibility that the KBC void is not unique, that there are other voids of similar size scattered across the universe, and we just haven't mapped them yet because they're farther away and harder to detect. If that's true, then the void is not a 10 sigma fluke. It's a common feature of the cosmic web that lambda CDM underestimates. Finding those other voids would be a game changer. It would shift the conversation from why does the KBC void exist to why do voids this large exist, which is a very different question. The first implies we're sitting in an unlikely place. The second implies the universe produces these structures routinely and the models don't account for it. DESI and Euclid will settle this within a few years. If they find multiple 2 billion light-year voids at various distances, lambda CDM is in serious trouble. If they don't, if the KBC void turns out to be genuinely rare, then the question becomes, why are we sitting in it? And that brings us back to the uncomfortable territory of selection effects and anthropic reasoning. Selection effects are where science bumps up against philosophy. The anthropic principle, in its simplest form, says that the universe must be compatible with the existence of observers, because if it weren't, there would be no one around to notice. Applied to the void, the anthropic argument goes like this. Maybe voids like the KBC void are rare, but they're the kinds of places where galaxies like the Milky Way form. Maybe the isolation, the reduced gravitational chaos, the slower pace of structure formation creates an environment where stable spiral galaxies with long-lived stars and rocky planets are more likely to develop. If that's true, then observers like us would naturally find themselves in voids, not because voids are common, but because voids are where observers tend to emerge. It's a selection effect. We're here because here is the kind of place that produces us. That argument makes some physicists deeply uncomfortable because it feels unfalsifiable. You can't test whether observers are more likely to emerge in voids unless you have a large sample of universes with different void distributions and can check where the observers end up. We don't have that. We have one universe, one sample, one data point. But the argument is not entirely useless. If future surveys show that galaxies in voids are systematically more likely to host planets, more likely to have low rates of supernovae and gamma-ray bursts, more likely to maintain stable environments over billions of years, then the anthropic explanation gains weight. It's still speculative, still untestable in the strict sense, but it becomes plausible. And plausibility, in the absence of a better explanation, is sometimes the best you can do. The KBC Void also raises questions about the ultimate fate of the universe. If dark energy dominates in voids, and if voids are growing over time as matter continues to drain into filaments, then the universe's future might be voidier than its present. Billions of years from now, the cosmic web will have sharpened. Filaments will be denser, clusters will be more massive, and the voids will be emptier, larger, more dominant. Eventually, as dark energy pushes galaxies apart and the expansion accelerates, the filaments themselves will dissolve. Galaxies that are not gravitationally bound to their local clusters will drift into the voids, isolated, alone, their light redshifted beyond detectability. In the far future, the universe will not look like a web. It will look like a scattering of isolated islands, each one a bound cluster of galaxies, separated by voids so vast that light will never cross them. The void we're sitting in today is a preview of that future. A glimpse of the universe as it will be when everything that can separate has separated, and the only structures left are the ones gravity can hold together. That future is trillions of years away. It's not something we need to worry about in any practical sense. But it's a reminder that the void is not static. It's part of a process. The universe is evolving. Structure is forming, sharpening, and eventually dissolving. The void is a stage in that evolution, a phase where the underdense regions are large but not yet dominant. In the deep future, they will be dominant. And any civilization that exists in that far era, assuming any do, will look out at a universe that's almost entirely empty and wonder whether it was always that way. They won't have access to the cosmic microwave background, which will have redshifted into invisibility. They won't see distant galaxies, which will have receded beyond the horizon. Their view of the cosmos will be limited to their local cluster and nothing beyond. They'll be living in a void without realizing the universe was once anything else. We're fortunate. We exist at a time when the cosmic web is still visible, when the evidence of the Big Bang is still detectable, when we can piece together the history of the universe from observations. The void reminds us that this window won't stay open forever. And that brings us to the enduring mystery at the heart of all this, our place in the cosmos. The question of whether we're typical or exceptional, average or unique. For 500 years, astronomy has been in the business of decentering humanity. We're not at the center of the solar system. We're not at the center of the galaxy. We're not in a special galaxy in a special part of the universe. The Copernican principle, the idea that we don't occupy a privileged location, has been one of the guiding assumptions of cosmology since it was formalized. The KBC Void complicates that story. We're not at the center of the universe, but we are near the center of the largest known underdensity. That's not special in a flattering way. It's not like being crowned the king of anything. It's like finding out you live in the least populated county in the least populated state. You're not important, you're just alone. But the fact remains that we're here, in this void, at this moment in cosmic history, looking up at the sky and asking questions about what we see, and the answers we're finding are shaped by the void in ways we didn't realize until very recently. The Hubble constant we measure is higher because of the void. The density we calculate is lower because of the void. The rate at which we think galaxies form, the timeline we've constructed for the universe's history, the models we've built to explain how structure emerges from the smooth plasma of the early cosmos, all of it is influenced by the fact that we're sitting in a hole. For a century, we've been drawing maps of the universe from inside an anomaly and assuming the maps were universal. The void says they're not. They're local, and local doesn't equal universal. That realization is humbling. It's also liberating, because once you know you're sitting in a biased location, you can correct for it. You can measure the void's properties, model its effects, and subtract them from your observations. You can look past the void's edge and measure the universe in regions that are closer to average. You can use the cosmic microwave background to anchor your understanding of the early universe and work forward from there. The void is a problem, but it's a solvable problem, and solving it will make our picture of the cosmos more accurate, more complete, more honest about what we're actually measuring and what it actually means. The next decade of cosmology will be defined by the void, not because it's the only question worth asking, but because it's the question that's forcing the field to confront its assumptions. Lambda CDM has worked beautifully for decades, but it's creaking. The Hubble tension won't go away. The early massive galaxies Webb is finding don't fit the timeline. The KBC Void is larger than it should be. Each of those problems individually could be noise. Taken together, they look like cracks. And the void is the largest, most visible crack, the one that's hardest to ignore. Whether it breaks the model or just forces refinements is the question the observations will answer. But either way, cosmology is moving, the ground is shifting, and the void is the fault line. The irony is that the void, this enormous underdensity, this 2 billion light-year hole in the fabric of the cosmos, has made the universe feel bigger, not smaller. Before we knew we were sitting in it, the universe felt mappable, understandable, a place where the laws were known and the structure was predictable. Now it feels stranger, more layered, full of features we didn't account for and effects we didn't anticipate. The void has expanded the space of possible questions. It's opened doors we didn't know were there, and whatever lies beyond those doors, whether it's a refined version of Lambda CDM or a fundamentally new understanding of how the universe works, we're about to find out. Because the tools are ready, the missions are flying, the data is coming in. And cosmology is not standing still, it's pushing forward, testing, measuring, refining, discarding what doesn't work, and building on what does. The void is the edge of our understanding right now. But edges move, and within a decade, maybe less, this edge will shift outward. The void will be mapped, its effects will be quantified, its implications will be understood. And cosmology will move on to the next mystery, the next crack in the model, the next question that makes the universe feel bigger and stranger and more interesting than it did before. That's how science works, not by answering questions and closing books, but by answering questions and opening new ones. The KBC Void has opened more than its share, and the answers, when they come, are going to be worth the wait. We started this story with a number that didn't match, a measurement problem, a 9% gap between how fast the universe appeared to be expanding locally and how fast it should have been expanding based on the physics of the infant cosmos. That gap, the Hubble tension, looked like a crisis, a sign that something fundamental was broken. Then we found the hole, 2 billion light-years wide, 20 to 50% less dense than the cosmic average, centered, for reasons we still don't fully understand, on us. The KBC Void is not a solution, it's a reframing. It says the crisis was never about the universe, it was about where we were standing when we tried to measure it. We weren't looking at the cosmos from a neutral vantage point, we were looking at it from inside a deficit. A place where gravity is weaker, where dark energy dominates, where space expands faster than it does in the crowded filaments and clusters that make up most of the universe's interesting real estate. Every measurement we made reflected that. The high Hubble constant, the low matter density, the slow pace of structure formation, all of it was local, none of it was universal. And for 100 years, we didn't know the difference. That realization doesn't just solve one problem, it opens a dozen more. If we're sitting in a void, how many other voids are out there? Are they common or rare? Do they grow larger over time, or do they fill in as galaxies drift back toward the filaments? Does the physics inside a void differ enough from the physics in dense regions that we need separate models for each? And why, of all the places intelligent life could have emerged, did it emerge here in the quietest, emptiest, least representative patch of the cosmic web within 1 billion light years? The next decade will answer some of those questions. Euclid is mapping 2 billion galaxies. Roman is surveying the infrared sky. Desi is tracing the three-dimensional structure of the universe across 11 billion years. The data is coming in, the simulations are catching up, and within a few years we'll know whether the void is a statistical fluke, a one-in-a-universe anomaly that we happen to occupy, or whether it's a symptom of something deeper, a sign that the standard model underestimates how large voids can grow, a clue that dark energy behaves differently in underdense regions, evidence that gravity